And this culminated in the ZK Warsaw Day 23 last year in a venue 4 times smaller than this one, and with way fewer participants as well. And so now, today, we are opening Verifiable Summit, the second full-day conference by ZK Warsaw. And I think Marek would like to talk about that.
Welcome, welcome. It's great to be with you today. And so that was Orest Tarasiuk, co-founder of T1 and original founder of ZK Warsaw, who we work together, and eventually we have the Verifiable Summit today. So we're super excited. We're super excited because it's very exciting times in the Ethereum space, in the blockchain space, and in the cryptography space, and we never hide our roots in the blockchain space. And we believe cryptography is in a very exciting moment where it will have more practical impact on our lives than ever before. And we're super happy because blockchain made it evident and make a lot of money flowing into the cryptography space. And thanks to that, there's so many fascinating topics we can talk about today on other conferences and things we can work on. And there is plenty of different themes that we're gonna talk about today. There is obviously zero-knowledge proofs, which is the frontier of the new cryptography front related to blockchain space, but not only to blockchain. We have fully homomorphic encryption, which is coming also to the blockchain, and it's also, we've seen a lot of breakthroughs in FHE in recent years. We have secure multi-party computations, MPC, which are already a huge part of advanced cryptography happening around the blockchain. And we have trusted execution environments. So that's something that's been around for a while, but now it seems there is a new wave of startups exploring what's possible with, in regards to practical application, where we can build a trusted execution environments. And then we have one more thing that usually is not talked about in the context of blockchain, yet very interesting, which is quantum cryptography, which we believe is also a little bit on the side track when it comes to the blockchain space, but it's a very mainstream field of research when it comes to cryptography in general. So we thought it's really important that we kind of help connect those two words together. Hence, we're gonna have some exciting talks about quantum cryptography. If that's something that you're not very familiar with, those talks should be simple enough to understand for the beginner cryptographers. And maybe that being said, it's important to say that we're gonna have all kinds of talk for the beginners, for engineers that wanna get general idea about how things work, and we're gonna have advanced talks for those who want to evolve their knowledge and skill set in cryptography, and then we're gonna have very theoretical talks as well, so everyone should find something for himself. Orest, to you.
Well, not really. It was Marek and Marek's team, Vileya, who knows the venue inside out, so maybe give us an intro.
Absolutely. So this is the main stage. We're gonna have, aside from the main stage, we're gonna have a side stage and we're gonna have a workshop room. So to go there, you have to go all across the corridor next to the entrance, and side stage is just in front. But to get the workshop is a little bit behind, so we have to go there a little bit from the side. There's gonna be screens, so there's gonna be information there how to get there. So you should be fine. If you find yourself in the need to go to the toilet, there is one just on the right, from this as exiting from the main stage. And if you're across the corridor, there is another one over there. You should be able to find it. It's next to the workshop space. And there's gonna be a lunch in the middle of the day, so that's gonna be right outside the main stage. So that's basically the area we're gonna go around, and it's a beautiful weather today, so feel free to, there is a wonderful patio, so feel free to use that, and yeah.
And if you don't want to use the weather, feel free to connect to the Wi-Fi and do some work. Yeah, you have the name here, and you can use the QR code. If it's not too small, it's probably too small.
Let's give 1 minute for everyone to make a photo or scan a QR.
And you get to learn some Polish doing so. It's kind of hard to spell these out loud.
Konferencja. Good. I'm looking at the room. There is still plenty of people making photos, so let's give it a few more minutes, a few more seconds.
We should have had photographers take a picture of the room as everyone is scanning.
Everyone is
this exciting.
Look how
project.
awesome we look. Everybody's making photos of us.
Okay, I think that's it. So now the agenda is not legible at all because we have such a packed schedule. We have 3 rooms. This is the main stage. We have the side stage and a workshop room that are a bit smaller. And you can go to verifiablesummit.com to be able to zoom in into the agenda. What I wanted to highlight is that there will be regular networking breaks at 11:30, so that's in 1.5 hours, and at 3 and at 4:30, on top of the lunch break at 1. So there will be plenty of opportunity to network, to get to know each other. And because of that, I'd like to encourage you to check out the talks as they unfold. This is the first time we're doing not 1, not 2, but 3 stages at once. And so we don't want you to miss out on those.
All right, and yeah, we would like to thank our sponsors, without whom we couldn't have made it. So Opacity, if there are Opacity people in the room, give us a wave. Woo. So Opacity is working, so there's gonna be a presentation and 2 workshops from Opacity today. They work on web proofs, so that's something we're also working on, so stay tuned. There's gonna be, so web proofs is a topic that was on everybody's mouth, it seems on everybody's mouth last week on Twitter. So we have 4 different presentations and 2 workshops about that, so stay tuned. And then we have Aleph Zero. Aleph Zero is building L1 based on ZK proofs, but also recently they started building layer 2, and we're gonna have some great talks from them. So make sure you don't skip on those. And Aztec Labs, who are building privacy preserving layer 2 for Ethereum, they also with us. So yeah, thank you very much, guys, for sponsoring, and we're looking forward to your talks. And just want to say, make sure you come to those, and yeah, give me a nice round of applause.
But that's not it. But just to speed up and not set a precedent of being late, we have base and starter sponsors, provably T1 and Golem. We also, since the early days, again, have been lucky to be supported by the ETH Warsaw team. We are an event that's happening 1 day before the main ETH Warsaw event. And still, we are very proud to say that we have speakers coming just because of ZK Warsaw or just because of Verifiable Summit. Still, ETH Warsaw has been an invaluable source of inspiration and experience to doing this, to making this happen. And also, we are proud to be supported by the ecosystem support program of the Ethereum Foundation, and that is always an amazing thing. And finally, a big thanks goes to Vilea, who's been so kind and so professional as to make this event, for me, it's very special to make this event fully hands-off for me. Like I didn't even know what the venue was, and this is so cool. I'm really grateful to you guys.
I think it's the last slide, is it?
It seems so. The slides weren't made by us either. So enjoy the rest of the event. We will start the first talk here and also in the other stages as per the agenda.
So I think the talk starts in 10 minutes. So we have a little of a break. So maybe I'm just gonna finish by saying what a wonderful weather we have today. And we're organizing this wonderful venue, which is National Library. and it's just next to Pola Mokotowskie, where there's a wonderful park. So after we finish, and if you still want to talk and still want to hang out, I really encourage you to explore Pola Mokotowskie, which is a huge park. Many of you probably know, but many of you don't. It's a beautiful park with lakes, with places where you can grab a drink, with places where you can sit, and bridges and all that stuff. So keep that in mind for the rest of the day. We're gonna have a beautiful afternoon as far as the weather forecast seems to be saying. So thank you one more time for coming and enjoy the show.
Hello? Attention? Okay, we're not starting yet, but next up we have Adam Gongul from LF0. But if anyone is interested in the workshops, there's also a workshop taking place in the workshop room on dissecting everyday TLS from opacity. Just make sure you're in the right room for the workshop or the talk which you want to watch next. Thank you. Hi, everyone. Please take your seat. The next talk is starting soon. So our first talk of the day is Adam Gongol from Aleph0, one of our lead sponsors. And he'll be delivering a talk on private DeFi, the possible, the impossible, and what's worth it. So please, everyone, give a big round of applause for Adam.
Okay. Hello, everyone. I'm audible, right? Great. So thanks for having me. I'm Adam from Aleph0, and I'll be talking about privacy in DeFi, mainly focusing on economic aspects. So not the privacy in the sense government cannot track us, but rather privacy in the sense what properties can it give us in crypto markets. But before I do that, I need to introduce some framework just to abstract away the aspect of anonymity, because it's going to be in every of the designs I'm going to talking about. So I want to create some clean abstraction so I don't need to go through it every time. There is basically one protocol, crypto protocol, that is known for granting anonymity. This is called Zero Coin Protocol, and this is based for Zcash, for Tornado Cash Nova, Railgun, zkOS, which is our project dealing with anonymity. And roughly how it works is that there is a smart contract where all the system deposits are residing. There is zk snark verifier, and users are sending zk snarks, attesting for the fact that they are legit owners of some of the tokens in this grant deposit. So basically, this is the idea is to implement the Zcash, which is its own blockchain based on this premise, in a smart contract layer of various chains. And that happens, this project that I listed are doing that. So we're going to refer to any such implementation of Zero Coin Protocol as a shielder. Shielder as a name for this primitive that can be used to grant anonymity. So the first corollary here is that it may seem that anonymous DEX is some kind of a big milestone or holy grail of privacy in DeFi. So it is not, because it can be created basically by merging shielder and regular DEX, such as, for example, Uniswap. So how would that work then? So there is some user which owns some private tokens of type A in the shielder and would like to exchange them to tokens of type B and also redeem them into the shielder. So, well, what should the user do? The user should initiate the transaction from the shielder to a normal, regular, public implementation of Uniswap. Then the tokens would be exchanged, and then they would go back to the shielder. There is a small technical caveat that actually he would need one-time account in the middle, because like there is some unpredictability in how many tokens B we get from Uniswap, because like someone can front run us, like the prices are changing, and for technical reasons we need to know exactly how many tokens we put into the shielder, because we need to construct zk proof based on it. But generally the rough pattern is like this. So all our funds are in the shielder. We can initiate from the shielder interaction with any smart contract, and we can get back all the tokens we get from the smart contracts back into the shielder. So this grants us anonymity. This does not grant us privacy. So it may be worthwhile to think like what can be seen from outside in this interaction. So like for any outside observer, this interaction looks like, well, the observer can see that X tokens A have left Shielder, the observer can see, of course, what happens on Uniswap. The observer can see that, that this tokens B entered the Shielder again. What the observer cannot see is which of the users have done it, and basically this action is absolutely unlinkable to every other action initiated from the Shielder. So it is perfectly anonymous and like in the pretty strong unlinkability sense, but from the economic perspective, all the details about the transactions are known and they are public on execution or actually even before it. So like if someone sees a transaction in the mempool, like it's gonna be very apparent what this transaction is trying to economically achieve. The only thing that is hidden is the user creating it. So what else could we possibly want from privacy? So, well, as I already hinted at the beginning of the talk, all kinds of economic benefits. So what are these all kinds? More on this on later slides. One more thing. So just to kind of debunk the very simplified view of the goal of the Holy Grail. So this is the design of impossibly private AMM. So like one could think that, okay, so maybe let's somehow cryptographically create a version of Uniswap where everything is super private. So like the amounts being traded are concealed and never revealed, and everything basically happens besides this cryptography curtain. So it is not possible, and even not from cryptographic reasons, but just from logical reasons, from, let's say, mechanism design reasons. So if we would have it and have some private execution engine for this Uniswap, let's say it runs in trusted execution environment, then what could happen? I mean, it could offer this kind of capabilities. So user could have tokens in the Shielder, then user would send it to the TEE. Some private execution would happen then, and user would get tokens B in return, and no observer could learn anything by just looking at the chain. The problem is that from the very fact how AMMs are working, adversary could sample it often enough to get a glimpse of what's going on. I mean, for every current AMM, there is a deterministic function mapping between the state of the pools inside of AMM and the prices and the trades that are happening. So adversary watching how the states of the pool are changing, for example, right now it's less ETH, and right now there is one more ETH and 2,400 less USDT. So, well, if adversary sampled these two time points, it's pretty apparent that someone just did a trade and traded one ETH to 2,400 USDT, because like one of the pools went down, one of the pools went up. So while this would, I mean, yes, there exists in theory some cryptography that could give us such design, but it would not achieve what we are striving to achieve. This thing is unachievable. I mean, AMM with full privacy. What is achievable though? Oh, yeah. So this kind of attack, this exploit works only for AMM. For order book-based exchanges, I mean, it's not so easy to sample order books. When it comes to AMMs, one can just do 1 epsilon of tokens and trade it, and then sample the price. For order book, to actually know what orders are residing in the order book, to learn this, the adversary would need to do a substantial trade. So this argument just doesn't work for order books. And hence, there is an idea of ideally private order book, which is theoretically possible. Right now it's cryptographically rather not possible for efficiency reasons. So again, there is a Shielder in the middle, and what users are doing. They are creating orders, or like how people tend to speak now, intents. So they are intending to sell X tokens A for B at price P, and then there is the other user with the perfectly opposite intent. What they do is that they are sending this intent to some kind of private matching engine, which can be just an execution environment again. This engine is matching the intent of one user to intent of other user, does the execution, and resends the tokens. So what can be this private matching? Well, so I'm aware of two approaches. One is TEE, which is what T1 is to some extent doing. And the other is multi-party computation. So this is the primitive that Renegade Finance is playing around with. And they are also they are cutting some corners. This is not this perfect design, but basically Renegade, I think, is the closest to achieving this kind of a private matching exchange. Okay, so this was maybe a bit long introduction. So right now, I wanted to set up a stage telling what is possible, what is impossible right now. So maybe now I'd like to say a bit more about what is worth doing and how to actually capture this economic benefits that privacy can bring us. So I split them for two categories. The first one are benefits of short-term privacy, and the other are benefits of long-lasting privacy. So when it comes to economic advantages of short-term privacy, these slides will basically be universal enough that they describe both TradFi and DeFi. So why it's important, maybe before going into the slide, why it's important to discern between this short-term and long-term privacy is because some cryptographic techniques can be pretty safely utilized to give short-term privacy, not necessarily so much to give long-term privacy. Like trusted execution environments are perhaps the best example here. So like whoever is following Twitter knows that there was an exploit just a couple of days ago, and generally like every year, or maybe not every year, but pretty often on Twitter there are these massive exploits where someone is hacking TE and extracting the master key or doing some other evil stuff. So if we would use this primitive to grant long-term privacy, that probably wouldn't work, because like eventually someone would find an exploit and steal these things that we wanted to be private forever. When it comes to short-term privacy, well, so these hacks happen, I don't know, once a year, maybe once a couple of years. So if we would use TE to grant privacy with a deadline of, I don't know, 5 minutes, then it's probably okay. I mean, no one is hacking TEs so fast. So back to these advantages. How the regular situation in order books, like without any clever designs, work, and that's how it works in TradFi, how it works in DeFi. The only difference is timescale. In TradFi, it's roughly 100 times faster. Almost everything is 100 times faster. Is that there is some Joe as a regular Joe, not trader Joe. So this is the user that is not arbitrager or like informed trader. This is the user with the actual need of exchanging one token to the other. So like we can even think, I think it's a good idea to think about DEX designs in a way that what we want to optimize is the price for this regular Joe, for user with the actual need of exchanging one token to the other. If we have an incentive design that gives good prices to these users, then that means that, well, we achieve some kind of incentive compatibility. So what happens is that, well, there is some state of order book that usually looks something like what I pictured here. So there is the further from the middle, the more liquidity depth, and usually there is almost empty area inside, and this is where all the trading is actually happening. The prices are usually not shifting very fast, so like all the trades are usually being crossed and matched in the middle. So let's say that Joe is putting a relatively big order, which looks like this. So what happens then, usually, is that there are informed traders or arbitrators which see this trade and think, well, yeah, maybe there was no liquidity inside, but actually it's a buy order, pretty close to the sell orders. This is something that we can profit from. So, so what they do is they are racing to get this order. So they are putting their own orders in order to be crossed with the order of a Joe. And, well, this is okay. I mean, competition is good. What's bad here is that this competition among these informed traders is purely based on speed and not on the quality of what they offer. So that is true both for TradFi and DeFi. And in DeFi, it's like whoever gets first in the block, usually this one would be, I mean, in such an order book without any special mechanisms, whoever gets first in the block is matched with this order. So, well, it's not terrible. So Joe have put some specific price on the order he created. So, well, the worst can happen is that he's gonna sell the tokens exactly at that price, and well, 99% of the times that's exactly what's gonna happen. Which is actually not perfect, because what we would rather want is these informed traders competing in value. So trying to propose as good a deal for a Joe that he gets more than he asked for. And then optimally, we would choose this one of the informed traders' proposals, which gives the biggest value to the Joe. But that's just not possible without any specific mechanism for that. And the specific mechanism is called FBA. This dates back to, I think, 70s when it comes to TradFi, and is relatively new to DeFi. So the idea here is that there is no, like here, sorry, here we had a direct link. So like Joe was sending the order directly to the order book. So no longer the case in FBA model. So Joe is sending encrypted order to the batch. Then there is mechanism which decrypts the entire batch altogether, and only then individual orders are landing in the order book. So why so complicated? For Joe, actually, this is kind of irrelevant. I mean, Joe is not specifically racing against anyone else. He's got like his specific order in mind, and most probably he should not care about whether this order is batched with other orders or not. There is some idea called coincidence of wants, but like statistics show that actually this doesn't work, and like Joe could hope that in the batch there would be opposing order, and so they would be just directly matched. But well, in CowSwap, which is the biggest platform doing similar batching, this almost never happens. So, yeah. And then the important thing happens. So these guys that are now racing to get the order of a Joe, to get matched with the order of Joe, what they need to do, they need to submit encrypted orders into a batch. So no longer a time race. Like the only thing they can do is submit a good proposal, because then what's going to happen is the entire batch with all the proposals of the traders will be decrypted together, and then what's going to be matched against the order of Joe? Well, the one which gives him the biggest value. So the competition shifts from the one where they are just racing based on speed to the one where they actually need to submit proposals that are valuable to Joe, and the one with the biggest value wins. So this gives more effective market, and definitely if we would define this loss function as, well, we want to be as good to Joe as possible, then this design achieves it better than the previous one. Then one could ask, well, why is the batch encrypted? So this may be not apparent at the first glance, but how it works actually is that this is kind of a blind auction. So informed traders are putting their bids in blind, and only then the best one wins. Otherwise, it would be not terrible. For example, Ko-Fi does not have this blind auction, and the proposals of the servers are public. But generally, there is this problem that these arbitrageurs could try to backrun each other and input a proposal just at the end of a block that is marginally better than the other proposal. So they would attempt to win the batch, not by giving the best solution they can offer, but just by giving slightly better than the others. So still better than the previous design, but not optimal. I mean, it not necessarily would find the optimal counter trade for what Joe was wanting to trade. Okay, so that's FBA, and usually, like, to kind of get an idea about the time scale, in TradFi, the time scale is usually something like 50 milliseconds for batch, but TradFi is fast. In DeFi, well, there is no FBA in DeFi yet. Ko-Fi, as I said, is relatively close design, so one batch is usually one block, so like 12 seconds. The difference is pretty big also because in TradFi, in every batch, there is substantial number of the actual trades that gets executed. In DeFi, like platforms, Ko-Fi is by far the biggest intent-driven platform right now, and in the average amount of transactions in a batch is 1. So, I mean, it still gives value because Ko-Fi is a bit more complex, and there is an idea of proposals that finally do not end in a batch. So there are solvers which are submitting something, and only the best one gets to the batch. And there is also split between users and solvers. But generally, we don't have like a massive volume when it comes to the number of trades there yet. So definitely some of the advantages that exist in TradFi would be still lost in DeFi due to the lack of volume and lack of this, let's say, cumulative effect of a batch. So this is like the theoretical model, and when it comes to more extended privacy, this is something that we are working on. This idea of reveal conditions. So the idea how the model works is that now Joe wanting to create the order, creates the order. So for example, this one says that Joe wants to sell one ETH to 2,400 USDC, and there is some specific reveal condition there. So this order is encrypted until the reveal condition is satisfied, and only then there is like the decryption committee that decrypts this particular order. And then periodically, which is important, so there are specific points in time where this happens, this committee checks which of the reveal conditions on the list are satisfied and reveals these respected orders in a batch. So aggregates all the orders with satisfied reveal conditions and decrypts them all together. So why we think it's nice? So first of all, FBA, so the previous slide, can be easily implemented this way. So the only thing that needs to happen are these arbitrageurs submitting orders with trivial reveal conditions. So orders like reveal me now, reveal me ASAP. So whenever there will be next point of reveal, all this order will get revealed and the best one will win. So FBA is pretty clear in this model. Users can create iceberg orders. Iceberg order is the idea from TradFi where one can create the order of which the vast majority is invisible. So like an iceberg, only the top is actually visible in the order book, and the rest of the iceberg is programmatically guaranteed to be also traded, but is hidden from all the observers, including, of course, other traders. So only when the top of the iceberg gets traded, then some other parts of the iceberg go up. So how can it be done? Well, we can use reveal conditions, reveal this order, only some other order is finally traded. So like this captures this idea of the like refilling orders, and we think that it's particularly interesting for DeFi because comparing to TradFi, we see that it's for many users much harder to automatize actions in DeFi due to this thing that like not your keys, not your tokens. I mean, people are rather more conservative when it comes to giving access to their capital, and well, also having a server running with a private key, which would automatize something, it sounds kind of risky. So we feel that it gives a good value that this kind of primitive can be fully automated on chain without the necessity of having the process resubmitting transactions, for example. Yeah, this is basically the third point, that it allows to automatize non-trivial actions without the need of doing basically anything with a private key. So like user can just submit some bunch of this transaction with various reveal conditions, and then it's done. I mean, this is a framework to automatize these actions by submitting the transactions and well, waiting until they get revealed and solved. And this is the final slide. So if there are any questions, I'd be happy to answer. And yeah, thank you for having me and listening.
I think we can take maybe one question if someone has one. Go ahead.
So mine is a very simple question about the reveal condition. Who reveals exactly?
So our idea is the reveal committee. So all the encryption is a threshold encryption. There is a specific committee, and there needs to be supermajority in the committee for the reveal. I mean, they need to use their shares of the key to reveal the condition. There is also this caveat. I mean, like it's easy to create economic mechanisms here to disincentivize malicious reveals. So, for example, if the condition is not satisfied, whoever shows the part of the decryption from other user gets some parts of the funds of the collateral put by this node.
Okay, we'll take one last question from the man in the green shirt. Can someone get him a mic?
So the reveal conditions are only enforced by economic and not cryptography reasoning, right?
I mean, it's a threshold encryption,
Yeah,
but yeah, I mean, like in the end, yes, there is a committee behind it. So in theory, the collusion in the committee could reveal whatever.
Thank you.
Yeah, but like that's the same model at which majority of bridges are operating, and I guess it's proven to kind of work. Yep.
Okay. Thank you so much, Adam. Very interesting talk. Yep, everyone, please give him a big round of applause.
Thanks again, everyone.
Okay, next up we have Hendrik Eckhout, there he is. And he's the TLS Notary team lead at Ethereum Foundation, and he'll be giving a talk on verify private web data with TLS Notary. Big round of applause, everyone, for Hendrik.
Good morning. Thank you for the kind introduction. So today I will introduce TLS Notary to all of you, and figure out how we can share and verify private data on the web. So, short info about me. I'm Hendrik. My Twitter handle is HECOW. I'm the team lead of the TLS Notary team, which is a research team in the Privacy and Scaling Explorations Lab, which is a part of the Ethereum Foundation. So the overview for today, a little bit cryptic, but I start with the why, what exactly TLS Notary is, how it works, and where and who, where you can use it, who can use it, and to make it prove that it actually works, I also have recorded a few demos. So first, why are we building TLS Notary? And it's all about portable data. So Alice has access to some of her data on a website. She logs in, gets her data, and gets it through HTTPS. And the question is, how can Alice share that data with Bob? So what kind of information could it be? This could be like any private information, like identity information from a government, financial information from a bank, private messages, but it could also be gaming assets or whatever. And then why would Alice want to share that with Bob? Maybe Bob needs to do KYC or wants to give a loan to Alice. All these kinds of information where Bob needs to know that the data that Alice shares is true. So Bob needs to be able to verify the authenticity of the data. So HTTPS is built on TLS, so it's a security protocol with encryption. I assume most of you use it every day. But so TLS provides authenticity. So Alice knows that the data comes from the website and not from somebody in the middle. So that's through certificates. It also knows, because of the key exchange, that the data she gets is has integrity, so nobody changed it along the way. And also, because of the encryption, Alice has privacy. Nobody can eavesdrop between the website and Alice. But unfortunately, what TLS does not provide you is portability. So I'll go into that in more detail later, but so TLS uses symmetric encryption. So once the data is on Alice's computer, Bob does not have guarantees that Alice didn't change anything to it. So in a nutshell, already pitching TLS Notary. So TLS Notary is a protocol that has all the advantages of TLS and also adds portability. So it's a way for Alice to share data with Bob so that Bob can verify the data. So Bob does not need to trust anybody else, but maybe except for the data on the website itself. Also to the website, it's invisible that TLS Notary is going on, and there's also privacy guarantees that I will dive into in the next minutes. But the whole advantage of doing all this is that actually all existing data on the web becomes composable. So without approval from websites, you can kind of assemble and collect data the way you as a user want, and then get services based on that data. And that enables a whole lot of new applications. So let's take a few steps back and talk again about why can't Bob trust the data that Alice has, because it was encrypted at the server side. So the thing is that Alice and the website use the same key. So it's symmetric encryption. So once it gets onto Alice's computer, Alice could like change the data and use the key again to sign it or something. But so that doesn't work. So Bob, if there's any meaning to the data, needs more guarantees and need to be able to verify that the data is correct. So what are some systems to do that? You could like use like public key encryption on the server side. So the website just signs off on the data with asymmetric encryption. That would be a very elegant solution. And then you just use some ZK proofs and everything would be done. But unfortunately, the big disadvantage there is that the website needs to cooperate. And in practice, there is very little incentives for the websites to do the extra work. It also might have more implications. So that's not something that I expect to happen soon. I hope it will in the end. That's actually the end goal of TLS Notary, but there's still a lot of steps to take. Another option that is used very frequently today is OAuth. But again, that requires cooperation of the website, and it also adds more assumptions, like now the OAuth server could censor, the OAuth server knows what you're doing, and some more trust assumptions there. Another option is to involve an intermediary. So Alice could query the data through this intermediary, and then the intermediary could sign off on what it had seen, and then if Bob trusts the intermediary, then he also knows that the data is authentic. So the advantage is nothing needs to change on the web server, but of course it's one intermediary, so the website could like easily block that intermediary if he doesn't want this to happen. And of course there's also trust assumptions again for the intermediary. So what we propose is to use multi-party computation. So that Alice and Bob needs to cooperate to get data from the website. And the advantages are clear. So the website doesn't need to cooperate. Privacy is guaranteed because Bob only sees encrypted data. And it's also secure because Alice cannot fetch the data and then share it with Bob if she tried to cheat in the protocol. Of course, it's also not free, so it will add more latency to the connection to the website. And of course, there's because of MPC in its current state, there's also a lot more bandwidth between Alice and Bob than just the bandwidth for fetching the data. But that's a lot of work in progress, so we're improving that part as we move forward. As in the previous slide, I said Bob only sees encrypted information. That wouldn't be useful. So what it actually means that after the TLS session ended, Alice can share unencrypted data with Bob, because there's commitments to the encrypted data. Bob can verify that this happened. And in that process, Alice can redact certain parts of the transcript. So for example, if there is authentication tokens or anything in the headers, or if the Bob, the verifier, only needs to know a username and nothing else, then you can redact everything except for the username. And also, this can be further enhanced with zero-knowledge proofs that instead of just sharing your address, you prove that you're not in the US, or instead of sharing your birthday, you prove that you're 18 plus. So that's at the use case side. So to summarize already what I did in the introduction, so a TLS Notary solves a conceptually simple problem. So how do you query web servers and share the data with another party in a way that's secure, verifiable, and privacy preserving? So let's take an extra step and see how exactly that MPC TLS works. But before we dive into MPC TLS, a short recap on how TLS works first. So there's a key exchange first. So that's with elliptic curve Diffie-Hellman. So Alice shares her public key with the server shares his public key. Then they do this key exchange and both derive a session key. And so this session key is this symmetric key. And once they have this key, then Alice can do a request encrypted with the session key, that the server can decrypt it, encrypt the response, and send it back to Alice. So how does it work in TLS MPC? So note that I will, from now on, I will say prover instead of Alice, and I will say verifier instead of Bob. So here we follow a different scheme where the verifier first shares his key with the prover. The prover shares a combination of the prover key and the verifier key with the server. And then the server just sent his public key back. And then we do an MPC, so a multi-party computation, where the prover and the verifier calculate the session key together. But in the end, instead of the prover or the verifier having this symmetric key, they only have a key share. So they can only encrypt and decrypt messages with the server if they cooperate. Also note, so I've put this MPC box there. So that's not a computer that's there in the middle. It's more kind of a hallucinated computer. So this is actually the prover doing computations on his side, exchanging messages with the verifier, also doing calculations there. So it's actually like oblivious transfer and garbled circuits behind the scenes to do all these calculations. So how does encryption then work with MPC TLS? So it's an MPC where on the prover side, there's the prover's key share and also the plain text of the request. So that's mostly a HTTP request. And on the verifier side, it's the verifier's key share as private input. And through this MPC, they come up with the encrypted text, which is the ciphertext. And then something I didn't show in the previous slide, it's you don't simply send the encrypted text, you also add a message authentication code there, which is kind of like a checksum, which is a G-hash here. And then so you also have to calculate that and then have the authenticated ciphertext. The way this works is that the prover cannot communicate with the server without the verifier's cooperation. And because the verifier participates here, in the end, when he gets the data back, he can verify that there was no cheating going on. Decryption is very similar. So prover and the prover receives the ciphertext from the server. That's as input for the MPC, but the key shares, they check the message authentication code. If that is correct, then it's authenticated and they can do the decryption. And in the end, only the prover sees the plain text, but of course the verifier has seen the encrypted text, and because of during the decryption, it also got commitments to all of the bytes that were exchanged. So in a nutshell, so prover and verifier have to work together to do encryption, decryption. The verifier cannot see the plain text, and the prover cannot forge requests nor responses, and also only the prover communicates with the server. So from the server's perspective, this is the same as any other TLS connection. So I've prepared a quick demo for this, where in this scenario, there is a prover which has access to the Star Wars API server, and the verifier wants to get information about Luke Skywalker, and the prover will share that, but it will redact the home world. So let's hope this works. So I have the prover on the left and the verifier on the right. And so I start with running the verifier as a command line server. And on the left, I have the prover in a web browser. And so the first thing that happens, there's a lot of text scrolling by, but that's the multi-party computation setup. So that's exchanging input for the garbled circuits. And then once that setup is complete, they start communicating with the server, exchanging keys, and then also doing the encryption and decryption. And then in the end, the verifier gets the redacted data. If we zoom in here on what the verifier saw, is that we have an encrypted header there, and also in the JSON you see we did redact the home world. So where is this applicable? So anywhere where you need to share private information. So this could be identity, but also financial information like records from your bank, or that you own certain stuff, and also social things. But there's actually a very wide range, and I leave that to your imagination. And I'm also very curious to hear what you come up with. But so in a nutshell, everything, all data becomes composable that way. TLS Notary is already used in a few very nice applications. So for example, ZKP uses TLS Notary to prove transfers on Revolut, to do to exchange on-chain tokens. Another example is OpenLayer, where they made this fun application where you can prove your gains or losses on Robinhood. So you proven returns on your investments there. Also, Opacity Labs, a sponsor here, made this very funny app where you prove genetic things from 23andMe. So you could have your baldness score or your Neanderthal percentage, but talk to them or go to the workshop later today to learn more about what they're doing. A refinement here. So until now, I've only spoken about 3 parties: a server, a prover, and a verifier. But in a lot of use cases, there's multiple verifiers that want to verify the same data. And just doing this whole dance over and over again might be too expensive. And so in that case, it might be interesting to delegate the MPC TLS verification to a third party. And that's where the notary in TLS Notary comes from. So you have a separate party just doing the MPC TLS, and then the sharing of the data is done with the verifiers. But note that in that case, it's a signed attestation. So it was delegated verifiability here. So verifier and the need to trust that the notary actually did the MPC TLS verification. Because the notary signs off, it attests that it saw that the MPC TLS transaction was authentic, but the notary key could be used to sign whatever. So always be careful if you just get a random proof. In that case, you need to trust the attester. I also recorded a demo of this setup. In this case, the prover will prove that he received a direct message. It will be notarized by a notary server we ran, and then you get a JSON file for the attestation, and then that attestation will be shared with a verifier that will just visualize that DM. So let's see. Oh, you can mute the audio. So in this case, we use the browser extension for TLS Notary. So we install a plugin for getting a Twitter DM. And then when you start this, it opens a side panel. It guides you to the Twitter website. It checks and uses the cookies there to do the requests. And then we see something similar as we saw in the previous demo. So we do the whole MPC dance. And then in the end, we get an attestation, which is for now just a JSON file, but that format will change. And then you see like there's encrypted headers, and then no redactions in the response. And now we will open a demo website. We have explorer.tlsnotary.org that you can also use to visualize data in proofs. So again, if we zoom in, we see the sent data and the received data. And then you can see that the DM is in there. So that was just to show that TLS Notary, it's a Rust library. You can run it natively or through WebAssembly, run it in a browser. We're working on this plugin system because the challenge is always how do you get the cookies or the secrets to do the response to get the private data, and this browser plugins helps you with that. So most users already do log in into Twitter servers or whatever the data is, so you can reuse the cookies in that system or to get the secret headers you need to do the requests. And so that's a convenient way to do it. One thing that's a disadvantage of using TLS Notary in a browser is that the browser cannot do a TCP connection. So to work around that, you need a WebSocket proxy, but that's easy. That's also something a user could run locally, or you could use a hosted service for that. But please play around and see what you can come up with. So TLS Notary is an open source project. It's dual licensed, so you can pick either Apache or MIT at your option. So it's written in Rust, and you can also, through a WebAssembly, use it in browser environments, and we have a browser extension that we'll work on that makes it easy to extend TLS Notary to use it for your specific use case. So getting started, we're very eager to learn about all the ideas you have. We have a quick start that helps you to do some experimentation either in Rust or in the browser. And to summarize, if you want to query web servers and share that data in a verifiable way, where privacy is also important, then use TLS Notary and give us your feedback. So here again, the pointers. So, thank you.
We'll take any questions from the audience. Okay, let's go with you there in the gray shirt. No, that one.
I wanted to ask about that hallucinated machine, like you called it. So a party that is going to actually touch the shard of the both prover and verifier and do necessary computations. In the real world, who is that party, and do we need to trust it as a prover or verifier?
Sorry, I missed the first part of your question.
Okay, so I wanted to ask about this party that you called the hallucinated machine in the first part. So the party that is going to touch the key shard of both prover and verifier and then do some computations on it. Who is going to be this party in the real world? And also, do we need to trust that party?
So in the real world, it is the two parties. It's the prover and the verifier. And so the prover only sees his secrets and the verifier only his secrets. And then it's like a cryptographic protocol where they exchange messages. So oblivious transfer is like a way to share information while keeping secrets. But it's a bit too complicated to...
So there is no third party, actually.
No, that's the hallucinate. It's like it's easier to think of it as this thing computes something, but that thing doesn't exist. It's that's the encryption, the MPC that's doing that.
Okay, thanks.
Yeah.
Okay, and I think we'll take one last question. I think the man there in the hat. Okay. 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 Okay.
I'll be quick like that. We can have two questions. Can you give more details on the reduction part? Like when you explain that you know about Star Wars, but you don't know about the word, and you are just hiding it. Yeah. How do you do this hiding part?
So during the MPC TLS, the prover commits to bytes that he received or decrypted, and then the prover decides which bytes get disclosed to the verifier.
So I want to ask about a way which is probably too complicated for the prover, but I'll ask anyway. In the current TLS, you have a Diffie-Hellman exchange and you have symmetric encryption of the data. And the problem is that the prover cannot prove that this exchange, like, that the data was encrypted with this key without exposing their private key. Can't they use ZK to prove that the data that they got was encrypted by symmetric key, which came from the Diffie-Hellman exchange?
So it's symmetric encryption. So you could then, I think, just encrypt something else with that same key and have that proof. So it would be not be that wouldn't work. So it's interactive.
Okay, thank you.
Yeah.
Thank you. A big round of applause for Hendrik.
Yeah. And if there's more questions, I'm here all day, so just talk to me and we can discuss.
Amazing, thank you. And now it's time for the networking break till 12 p.m. And afterwards on the main stage at 12 p.m. we have Marek from vLayer Labs delivering his keynote. And please make sure to check out the agenda. There's also talks happening in the workshop room and the side stage. So make sure you have a look so that you can decide what you want to see next. Thank you. Okay. Sure. Yeah, you just like face like right before.
Are you ready? We are about to start. Only 100 people need to grab their drinks, and then we're good to go. 98 now. Maybe we test the remote. No. So now we know how the. Okay, it's working. It's working. It's not connected. Yeah. He hooks it up when 97, 96, 95. Uh-oh, 96 again. No, okay. He's just changing the row. That's fine. That's allowed. 93, 92. Only 91 people to go.
Natalia, could you pass me my phone? I'll check with the team if it's. Everyone in the networking room, please make your way to the main stage, the side stage, or the workshop room. Talks are starting soon. Everyone in the networking room, please make your way to a stage. Talks are starting soon.
Talk loud on Monday. Fast. 71.
Final call. Anyone in the networking room, please make your way
60,
to the main
69.
stage, side stage, or workshop room. Talks are starting soon.
So that's for insiders on. That's a reverse Bluetooth. You count down and stuff. Count down. Okay. Oh yeah. Totally. Alrighty then.
Hi everyone. Next we have Marek Kuricik from vLayer Labs, and his talk will be introducing the Verifiable Data Report, Select Insights with CTO Commentary. If anyone is still making their way into the main stage, please take a seat. Over to you, Marek.
Righty. Hi there. It's good to see you again. All right, we have a deck on. So yeah, I'm gonna continue. So I hope most of you were on the Henrik talk about TLS Notary. I'm gonna extend on the things he was talking about, and we're gonna talk about web proofs, which is more general, idea that TLS Notary is implementing. And I want to just mention that we're working on a 3-part report on verifiable data. And the web proof is going to be the first part. Then we're going to talk about email proofs. And then we're going to talk about on-chain proofs. So that's coming soon. The first part is coming this month. So if you would like to be notified when it comes out, you can leave your mail under the link or scan the QR code to get there and leave your mail. So we're going to go in detail about what the web proofs are, how we believe they're going to change the blockchain and the Ethereum and the wider blockchain ecosystem. So, yeah, stay tuned. So I'm going to talk specifically about the web proofs in the context of blockchain. So the Henrik talk was TLS Notary, how it works, but now we're going to try to connect it to the blockchain. And we're going to start with some use cases. I'm going to give you some examples to make it really something tangible, and we're gonna look a little bit under the hood. We ain't gonna redo the Henrik talk, don't worry, Henrik. And then we're gonna dive into different security models. What are the consequences of getting those proofs onto the blockchain? And then if we have time, then we can dive into protocol designer consideration, other protocol designer consideration than security model. But I would like to start with emphasizing the importance of web proofs, because if you think about it, where is the Ethereum today? Or again, Ethereum is my favorite blockchain. You can extend this to your favorite blockchain, and we're in the best place ever. The blockchain is legal suddenly. It was always this gray area. Now we have ETFs, we have MiCA in Europe. It's scalable. I remember just a few years ago, it was just, we're talking about scalability again. Nobody done it. It just doesn't work, you know. And now with L2s finally maturing, it seems like, yeah, we're almost there. Like, we have some work to do because all those L2s are not as secure today as we wish they were, but that's probably 1-2 years away. And it's more usable. We have better wallets than before. We have things that, you know, we can design transaction with our fingerprints. We can do all this great stuff. We don't need to know about fees, and all this stuff is slowly going away. But the feeling is something is still missing. Like the blockchain is still this, you know, there are important usages of the blockchain, like, you know, speculation is one of them, NFTs, DeFi, international transfers are a big thing, but it feels the potential is still not realized. And it seems we're lacking the mainstream use case. And I believe, and many people believe, that the reason is the isolation of the blockchain. If you think about the internet, if you think about Web 2, it's so strongly intertwined with our lives. We watch movies on the internet, we shop on the internet, we order our Uber on the internet. But when we go into this Web 3 world, it's suddenly very, you know, full of anons, and you need to bootstrap your new identity and figure out what to do with it. So the big question for me for several years now was, how do we connect one to the other? And this is where verifiable data comes in. This is where web proofs come in. And the big question one might want to ask, can we really solve the problem with even more technology and even more cryptography? And I think the answer is yes, we can. All right. So verifiable data, 3 different types. We talk about them, I talked about it already, so let's jump straight into the web proofs. So I'm gonna start with examples to make it a little bit more closer to real life. So perhaps the strongest connection today between the blockchain and the real world is real world assets. So we see growth of the various tokens that represent real world assets. That could be many different things. That can be just stable coins that represents something that is backed in the bank by fiat currency. But that could be really any securities. It could be shares of the company, stocks of the company. It could be physical objects. It could be real estate. There are companies now that tokenize yachts. So, and it's growing fast. It's the fastest growing subspace of blockchain. But But the problem is, a lot of those are not really, like, you just need to trust. We're losing all that permissionlessness. We're losing all this trustlessness assumptions for real assets. How can we improve on that? So with web proofs, you can say, I want to issue a token, right? And that represents your favorite security or real-world item. I'm going to call it Quackles, my tokens. And before I'm able to hit the submit button and issue a transaction, I need to log into my bank. And I need to go to the bank. And there is this plugin in the browser you can see on your right side. And it kind of guides me to the right screen. And then I click, it says the total balance is $2 million. I hit generate proof. Boom. And it takes a little bit. I go back to the application. The proof is already verified. And now I can submit transaction together with the proof saying, OK, you can issue 2 million Quackles or whatever is the item or token in charge. Obviously, someone can have $2 million today, issue a token, and disappear and make a transfer tomorrow. So we're going to need some kind of health checks, say daily, quarterly, whatever, balance sheet checks. That might vary a lot, what it is exactly, depending on what kind of real-world assets I want to issue. And it's never going to be fully permissionless and trustless, but we can get it to the trust minimized place, which is what we want to do. And another example, and this is interesting because kind of real-world asset already exists, but we believe there's going to be a new category of product, a new business model archetype created within a year or two that's going to be called Web 2 Web 3 markets. There is a great company, ZKP2P, that already was mentioned in the Henrik presentation, that is innovating. And Web 2 Web 3 market is a market that gets settled on Web 3, and you trade things on the in the Web 2 world, or maybe things in the Web 2 world in exchange for the things in the Web 3 world. In case of first experiment so that could be like things like, again, that could be securities. Maybe you want to trade your shares in the company, maybe your unvested or vested shares, or maybe you want to trade like virtual items, like game items. But in case of ZKP2P, it was an on-ramp, so it allows you to change fiat currency for the for the cryptocurrency. And again, it's very similar. You want to exchange $200 for 200 USDC. You pick your bank. You hit swap. You going off to the bank, generate a proof using this sexy plugin of ours, and boom, transaction confirmed, and you receive 200 USDC. And you can claim it. So those are two examples. There seems to be explosion of ideas. Last week there was, I think, at least 3 different tweets from 3 different people, Vitalik included, talking about different ideas. So it's coming. It seems we're going to have a lot of more of those. So just a quick remark. How do we fetch this data? We need to log into the bank. You need to log into the game. You need to log into all those different places. So the web plugin demonstrated by Henrik is a one way to go. And I think the nice thing about the plugin is we're already successful as a broader blockchain community in installing plugins into user browsers. So that seems like a reasonable way to go. I believe eventually we're going to merge plugins into wallets as the technology going to mature. And there's a little bit of standardization work to do in the meantime. I'm going to jump to the third one in my presentation, which is a server. I talk about the health check. I think that's going to be the enterprise, the B2B market. They're going to be looking more at the server. The least bullish, I think I'm about the mobile, because we didn't see any successful companies building either mobile browser plugins or applications that ask you to log in inside their application into different applications. So we'll see how the mobile goes. But this is the third option. All right, so under the hood, fasten your seatbelts. Are you ready? This is going to be fast because Henrik was already talking about it, so I hope you already know. This is a TLS connection. We agree on the naming. I think the transcript is the information being exchanged from the one side to the other. And pretty much every single data somewhere in the world is behind some TLS connection, an encrypted connection, whether it's HTTPS, and you know that S stands in HTTPS for TLS, and so on and so forth. Like almost every encryption today is encrypted, and almost every encrypted connection is TLS connection. So the web proofs in a nutshell is this idea that the client can take a transcript and take the transcript to the verifier in a way that verifier can be assured that this is really the transcript that happened from the connection between client and server, right? And TLS notary solves it, and this is pretty much how almost all web proofs work. It solves it in a way by introducing a notary. Notary is joining a client and connecting to the server, so they have this the kind of MPC algorithm having, and they all kind of taking half of the responsibility for making things happen, and only together they can make the connection happen, and only with the data from both client and notary, verifier can reproduce the transcript and hence be convinced that this is really the content of such a connection. And this is really where our story starts, is how do we transfer that information to the blockchain, right? So this is kind of where TLS notary story ends, and this is our big question as a community. How do we make those real-world assets, how do we make those Web2, Web3 market work by transferring this confidence of verifier to the blockchain? And that's a big question, and one first idea that should come to everybody's mind, why don't we just run verifier on the blockchain? Well, unfortunately, a verifier is pretty computational intensive thing, and even with the cheapest old tools and much better VMs than EVMs, that probably would be not feasible. So there is 6 ideas how to solve. There are 6 different security models I want to discuss today, or at least 4 I want to discuss in deep, and 2 more I want to advertise. So first is a naive approach where we trust the verifier or notary. It's kind of the naming thing, which one is which in this scenario. But we simply ask the verifier, hey, verifier, can you sign it for me and put it on the blockchain? The problem is verifier is a single point of failure, and he can get malicious, he can get hacked, so that's not a very good idea. So this is, by the way, important notion, also statement about where we are as a subspace of the blockchain. Everybody is using that today, right? So wherever you go to zkP2P or any other, this is what we're using today. This is not the final solution, this is what we build prototypes with, so keep that in mind before sending millions of dollars with a TLS notary to someone. Yeah. So, so the first idea is, how about we prove the verifier in the ZK prover? And then when we put that in the ZK prover, we already get some interesting security properties. So now the verifier needs to provide a transcript and a proof. The nice thing about this solution is that we can add computations, right? So when we're getting this server response, let's say it's a JSON or maybe in the future HTML, it's a little bit too slow today for the HTML, but could be very well ready for HTML in a few months. So how do we parse that and get all the information we want? And again, we can do it on-chain, but it's computationally heavy, like even a small JSON is like a kilobyte, sized in kilobytes. A little bit a lot to parse on-chain, but if you do it in the ZK, then you can just add these computations, which are pretty simple and compiled onto verification. So that's already have a really nice security properties because, and I'm gonna start with the second point here, is for the client, for the people who are using the protocols based on web proofs, it's already multi-sig 2 out of 2, right? So it needs to be, in case of real-world assets, it needs to be asset manager and a notary, then sign on something, right? And they cannot do it without themselves, right? So that's already so much better than multi-sig one of one, right? But the real big increase in security is on the client side. So the client, talking about HTTP client, so real world asset again, right? Because now the notary cannot do anything without the client, right? So imagine you run a notary and you have a bunch of clients and it gets hacked one day, you know, and you're not responsible for all them losing money. So that's a really big security improvement. And one thing is important. For that to work, we need to know who the client is, right? So if we are talking in the TLS, if we're talking about the asset manager case, well, the asset managers, we know who they are, right? We know what bank account they're gonna log in, we know what their address is on-chain, right? It's a little bit different for the cases like Web2, Web3 markets, because in that case, well, we don't know who the client is, so the malicious notary or hacked notary can just spawn a bunch of clients and drain the protocol, right? So it's really important protocol design and consideration. Yeah, so it's a very reasonable level of security for example, real-world asset stuff. A little bit more tricky for that Web2, Web3 markets. Then everybody talks about secure enclaves and trusted execution environments. And if I could get just one Bitcoin every time someone talks to me about it, I would have a lot of Bitcoins. So TEs are interesting, and they can improve security significantly, but not in a way that most people understand. So the first and most important assumption on TLS notary or web proofs in general is it's secure because client can do nothing without notary, and notary cannot do anything without the client, right? So it doesn't increase the security in a sense that a notary colluding with a client or spawning its own client, or hacked notary can spawn their own clients or collude with clients. It doesn't solve that problem, but it makes notary so much harder to hack. So that's an important thing, and there are two variants of that. We can run trusted execution environment on notary and verifier. So yeah, about TAs, everybody said, a lot of people say use TAs, but they get hacked all the time. And here is an interesting argument I heard a few times before, but not a single TE got hacked in a way that leaked the private key, hardware private key, the designs, right? So that should be good. That doesn't really matter in this case. Because the only thing we care about is they don't share the secrets, right? So not the hardware key is important, but the content of what's on the server or inside the enclave in this case, right? And there are some very sophisticated and expensive techniques for getting the private key if someone insists on talking about it. But all in all, it's a very expensive attack. It's available to big companies with, you know, the cost of such an attack is in hundreds of thousands of dollars, and maybe to the state actors as well. So not impossible, but not your script kiddie kind of thing. Yeah. Yeah. So that was variant 1, but variant 2 is interesting because you can kind of combine ZK with TE. And now ZK is responsible for making sure that client and notary, if they don't collude, then the result is okay, the result is verified, and TE is just making getting notary hacked very, very, very difficult. Yeah, so that could be a reasonable and I think this is a good moment to introduce the notion of black swan event. So when you design your protocol based on TLS notary, you don't want to have a black swan event that kind of withdraws all the money from your protocols based on web proof. So that could be like 1,000 users, each coming with their own web proof and withdrawing a little bit of money. That could all happen in a single block or in a few blocks, one after another. So that could be a single black swan event. So that's still tricky for that. But if your protocol doesn't have a black swan event, that could be very reasonable level of security. Then there is this idea to increase the number of notaries. So why not instead of one notary, we have 2 notaries? So that's technically possible. I don't think it would be technically possible to increase number of notaries to 3. because the overhead of notary is already 1,000 times, roughly 3 orders of magnitude. So when you exchange a kilobyte of data between the client and the server, that translates to roughly a megabyte of data between the notary and the client. So the TLS notary is working hard to push it down, and they believe they can push it down 1 order of magnitude. When that happens, you can exchange the main 2PC, 2 multi-party protocol into 3-party protocol, and introduce a notary, but that's gonna bump again the overhead. So we're probably not able to do more than that. But the interesting thing is we're basically bumping multi-sig 2 out of 2 into 3 out of 3. Well, that requires major changes to the protocol, so that's maybe a year or 2 years ahead of us. But that's really interesting idea, especially if we combine it with TEs. Like this is like attacking that would means having hacked into 2 TEs simultaneously, colluding with the client. Like that's getting really difficult. Not impossible, theoretically possible, but yeah, really hard. Good, and so that was the main 4 ideas, algorithmic or hardware-wise. And now we can talk a little bit, and I'm gonna just not try to explain the whole thing. Gonna give you just a brief introduction of some ideas, how we could do it, solve it by crypto economy. And I think the leading team comes with caveats. It's not that easy. Like when you start exploring. Like everybody started exploring, and I know we need the notaries, and they're gonna vote. Yeah. But then this and that, and it gets really complicated really fast. But there are those 2 ideas that seems to be pretty worked out. So this is idea coming from ZK P2P team that I mentioned already a few times. So if you assume 4 different additional security assumptions, which is incentivized counterparty, which means there's someone else in the system who is incentivized to tell the system that you cheated when you cheated, and he has the same access to the data as you do, right? So that's in the Web 2, Web 3 markets, that's usually the case because you have, another user of, if you're sending a transfer from bank to bank, from Revolut to Revolut, you have information that you send, and the other person has information that they received, right? Data immutability is an important assumption, which means if I keep querying my bank again and again about my transaction, it's still going to be there, and it's going to be same transaction. So this is a little bit tricky, but because even in the banks, transactions tend to change over time. And trusted notary majority, so we have a network of notaries, and we can trust them. And transaction value clarity, this is kind of optional. But when we know we're trading $100, that we can insure $100 for $100. If we're trading something and we're trading $1 million, but we don't know it's $1 million, and someone gets $100 in return, that's not really solving a problem, right? So the idea is to introduce the network of notaries, and basically it's an optimistic notarization, right? So when you want to notarize something, you just go to a random notary. You can pick yourself. It can be some process to pick that up, but I think you can pick yourself, or randomization is perfectly fine. And then if this incentivized counterparty says, hey, but I did send a transaction, right, or wherever is the opposite information, then you say, okay, I wanna start a dispute, and we're gonna settle, and you go to all the different notaries, and you do a settlement, and then the majority votes, and if the majority says it happened, when the notary didn't believe that happened, the original notary, that's the one that gets slashed, that's the one that pays insurance, and that's where property known as transaction value clarity comes in handy. Good. So the next talk is from Opacity. I ain't gonna talk about their stuff because you should hear it from themselves. But there is one more idea that's gonna be discussed next. So TLS notary and in general web proofs are very nuanced topics, and I hope I convince you a little bit that on the security side, it's not that straightforward, and we don't get perfect answers. We need to mitigate things. and get to a reasonable places. There is other consideration. There is a replay attack problem. So if you notarize something, how do we make sure it's not getting reused? So that can be solved by similar means as reply attack in Ethereum. So that has a few different shades. Just want to make sure it's in your head before you start building something. There is an anonymity consideration, and TLS Notary has this wonderful property that notary doesn't know anything about the content of the transcript, only the verifier does. So maybe one day we're going to be able to run those verifiers on our own machines in the ZK, or in different setups, we're going to be able to run on machines. So we're going to, on our own machines. So that's going to be wonderful for anonymity, because the only thing they're going to get to the blockchain is the result of the computation. So they don't know nothing about the original request, only about the result of computations. And finally, there is still there is a lot of performance improvements that have to happen across the whole stack, starting from MPC algorithm all the way to how do we settle that on the blockchain. And I think that's going to be a long ride, but we get to a place where it's really nice UX, and yeah. So that's another bunch of considerations that we have to keep in mind, that it takes, whatever, 30 seconds to notarize, another some amount of times to calculate ZK if you do calculate ZK. So that's something you should think about when designing protocols. Yeah, I think those are my extra slides, so I'm going to skip on them. Yeah, so web proofs are definitely among the most exciting technologies that are being built today, and new exciting use cases are coming. I hope everybody is convinced by now. We need a little bit more time to mature, and it's really important that protocol designers are aware of those security nuances and other nuances that comes with it. So yeah, stay tuned for the report, and stay tuned for what VLayer is going to be role in all of this. And thank you very much for coming to my talk.
Does anyone have any questions for Marek? Any questions from the audience?
My presentations are always so clear, there are not as
Are you stretching there in the hat, or do you have a question? No question?
Just stretching.
Just stretching. Okay, thank you very much, Marek. Everyone give Marek a big round of applause. And next we have Steve from Opacity, and he'll be delivering a talk on verifiable data. What is it? Why do we need it? And how Opacity makes it easy. And just as a reminder, Opacity is one of our lead sponsors. So please give a warm welcome to Steve.
Thank you. Yeah, as she said, I'm Steve from Opacity Labs, here to talk to you about our product and why we built it the way that we built it. Some of my first few slides here I can probably speed run through if my slides come up. There we go. So on socials, I'm 0xwildhair, if you want to connect with me. Hirsch was supposed to give this talk, so I wanted to start with a quote from him. We live in a world with a poverty of verifiability. I think that's very true. Very excited to see what possibilities we open up by introducing verifiable data to the world. It's just super exciting to me. We have the chance to change the way the internet works. We have the technology to do it now. We have lots of teams building really exciting infrastructure, and some apps that are starting to get built, and looking forward to see what gets built on that. The last two talks covered a lot of my first few slides, so I'll just sort of speed run through them. Verifiable data is something that's been signed off by some authority. Ideally, we'd be able to generate a ZK proof from that. And it'd be something with, enough integrity that we would want to, or we'd feel free to base economic transactions based on that, and our large corporations would feel the same way, that this would be basically rock solid. Why do we need it? We're building these hardened crypto economic systems. From that point of view, unverified data is essentially the same as noise. So we need verifiability to be able to use any real world data in a blockchain. It'd be real easy, Henrik mentioned in his talk, it'd be real easy if the servers would just authenticate the data themselves. If it came pre-signed, then none of this would be necessary. We could just use the data. There's some reasons that they don't do that and won't do that, or maybe eventually they will, but there's some liability reasons, and also there's some data that companies would not want to necessarily verify or share. For example, a lot of early blockchain, early Ethereum product ideas were things like decentralized Uber, decentralized Airbnb, which are still great ideas. But there's issues. One of those issues is a bootstrapping problem. If I want to run a decentralized Airbnb, it'd be real helpful if I could just port data from Airbnb. So if someone wants to rent their house on my network instead of Airbnb, or in addition to, if they could just transfer their profile over. Well, Airbnb's never going to provide that data willingly, let alone cryptographically signed to prove that this information's true. So based on TLS, the S in HTTPS, we've covered this a few times already today, but we've got certificate authority and end-to-end encryption, but it's symmetric encryption. Just quick sort of overview of how that works. We verify a certificate, we do a key exchange, and now we're free to exchange this encrypted data between the client and the server. That uses a Diffie-Hellman key exchange to derive an AES key. But like I said, it's symmetric. Both parties have that key. So the information that is exchanged, it's secure between those two parties. But outside of those two parties, I can't transmit that to a third party and have them rely on it because I had the encryption key. I could make it say whatever I want. So we've got to add some complications. So there's a few different options on ways we could do this. We could just offload the entire thing to a TEE. It's a hard trust assumption on the manufacturer, and as Merrick mentioned, the TEs have been hacked. We can proxy through an intermediary. A couple downsides to that, privacy being one of them, and also if you're communicating to another server through a data center, they can easily block that IP. And then the third option is to use MPC with garbled circuits and oblivious transfer. And at Opacity Labs, that is the choice we went when building our eigenlayer AVS that acts as a notary as a service. So bottom line, MPC is the best approach to building a ZK TLS protocol that's going to work at scale. good censorship resistance, it's privacy preserving, and it's probably legal in most cases. So, okay, are we done? Can we bring data on chain now? What's the point of having a cat if you can't use them for memes, right? So the problem is collusion. If the notary and the client, the user, if they collude, you can put any information you want into that, into whatever data you want. You can notarize it if you control both the notary and the client. So if we can't just do two-party MPC alone to have verifiable data that we can use on chain, then can we use more parties? Merrick mentioned this as an option also. But the bottom line here is, yes, it's possible, but the mathematics behind it just increase the latency to a point that it's not practical, at least not yet. We need some major improvements in the cryptography before this becomes practical for production. The problem being that your server request is likely to time out before we're able to do all the computations necessary here. So we're stuck with two parties. So now, what if we do it several times? What if we do, use several notaries and just do this two-party MPC dance over and over and over again? Well, problem here is that we can slash honest nodes. So we're running an AVS with operators. If an honest operator can get slashed under basically any conditions, we're not going to have any operators. So that's a non-starter. The reason behind that is if I'm proving a bank balance, right? And let's assume an honest user as well, right? I'm going through this MPC process. It's going through 10 different notaries. And let's say I switch over to another screen and buy something on Amazon or pay a bill or something. My bank balance changes partway through the process of running these multiple notaries. Then I have some notaries that report one value and others that report another. They could end up in notaries that are running their software properly, they're not colluding, they're not giving bad data. It could lead them to getting slashed, and obviously that's not going to work. So what can we do? As Merrick mentioned, we're using a identity-based approach. Another Hirsch quote here is a subtle shift in perspective versus cryptographic wizardry. I just like the way that sounds, but it's true. Instead of solving this with complex math, we're solving it very simply by paying attention to a history of requests. So out of all these possible notaries or operators that we have on our AVS, one gets picked at random. But before that happens, we make the user commit to a hash of the response that we expect to get back from the server. Once the notary's selected, they do the MPC scheme and prove the verification. Now, if they're trying to collude, if they're looking for a colluding node amongst our operator set, they can retry this over and over again. And then that'll look like what we have here on the right. We'll have a failed request, failed request, failed request. They finally land on the colluding node and, success. They get to say whatever they want and have a proof. The problem for them is that since we've been tracking these requests, we have a history of bad requests. And so we can just assume that they did this. We've got a bad operator in the set, and it's very easy to see. Since we're likely all crypto native here. Of course, the logical next question is, well, you know, addresses are free. Why don't I just spin up a new address for each request to prevent tracking that history? And here we do get to use the committee that I discussed earlier. We can have multiple operators verify a user ID for a specific server, because that's not going to change. So now we have a user sign-up process that essentially involves them signing into this server. So if it's Twitter, I log on to Twitter, and I let one notary see me do that. They sign off. We go through that process a few times. All the notaries agree, yes, this is the user identity associated with this account, and we can tie that back to this specific address. And now we can track those requests to that one address. And that brings us back to this history of bad or failed requests that we can monitor. You can see them on chain. The other notaries will monitor the history, and once you have a few failed requests, we're just going to stop receiving requests from that address. Okay, so cool. What do we do with it? Which this is a really interesting question. There's been some ideas thrown around already this morning, both by Henrik and Merrick. Lots of use cases. I'd really encourage you guys to think about things that can be built, because, you know, like I said, we're building infrastructure here. The applications built on top of it are going to be the really interesting part. I mentioned earlier the idea of basically a vampire attack on a existing network. We have one client named Nosh that's doing a Grubhub vampire attack. They'll let you port your Grubhub account into their account, so you have your full history, really knocking down the walls of this barrier to entry or this cold start problem. You can start with an existing network for your application. Another customer of ours is called Daisy. TikTok responds to the first 2 minutes of the algorithm, responds very much to the first 2 minutes of interaction that you get on a post. The influencers before were just using screenshots to show, hey, I liked, you know, I reacted to your post within the first 2 minutes. Using Daisy, that all becomes verifiable and solid. They've done pretty impressive revenue, actually using ZK-TLS proofs on TikTok. There's a guy who's starting a bald chat group in Farcaster based on if you can prove via 23andMe that you have the genes for baldness. I don't know what they talk about in there. Hats, maybe. But that's a thing. This is the screenshots from a sort of a toy app that we put together at Opacity, where you can look at your Neanderthal genes on 23andMe. You can prove if you traded GameStop on Robinhood during the GameStop craze, your Carta options. Basically, you know, anything that you can think of that might be useful that is data is available through TLS. And now with these new tools, and, you know, shout out to the Ethereum Foundation for building TLS Notary, because we rely very heavily on them. Shout out to Eigenlayer for building their infrastructure that we're building the AVS on top of. But all these tools, they unlock the ability to do something that we haven't been able to do before. And I'm just super excited to see what people build on top of this in the future. So does anyone have any questions?
Orest, what's your question?
Thank you so much. What do you mean by three-party or actually multi-party computation introducing latencies that be impractical? Any ballparks you could share?
I don't have that. I actually, I asked about that myself earlier with Henrik, and no. Just, it's something that's not practical now, and no real timeline on when that would be practical.
Thanks.
Yeah.
Any more questions from the audience? Okay, so I guess we'll wrap it up there. Thank you so much, Steve. Everyone give Steve a big round of applause. And thank you once again to Opacity for being one of our lead sponsors. And now it's time for lunch, and lunch is for 1 hour. I believe we have a buffet-style spread outside and more coffee and tea. And then at 2 p.m., the next talk on the main stage is FFTs on the projective line by Ariel Gabizon from Aztec. He's the chief scientist at Aztec, and that's going to be one of our big keynotes. So if you're interested in that, please join us in 1 hour. Thank you. Everyone, talks are about to start in 5 minutes. Please make your way to the main stage. Starting in 2 minutes, please make your way back to the main stage. One minute till talk time. Everyone, please make your way to the main stage. This is the only talk taking place at 2 p.m. There's no talks in the workshop room or side stage. Please make your way to the main stage.
Даешь микрофон, если что.
Не, я скажу, давай я отвечу. Строго микрофон. Так. Сложный алгоритм. В мою светлую голову это не попадает.
Не переживай, это же не блондинка.
Гламур.
Там типа вот эти анекдоты про блондинок, они очень прокрашены. Еще какие? Если она не абьюзит, это значит, у вас нет
Микрофон ничего не сказать.
Everyone, please make your way to the main stage. Talk is about to begin.
Yes. So I should be there, yeah? Ah, okay.
Inside all the time.
Yeah, okay. So I can sit like somewhere here, whenever.
Yes, you can sit here down probably.
Oh, wait. More at somewhere at the first line, or can be like there?
You can
or-
see the first lane, second lane, how's you wish.
Everyone, please make your way to the main stage. Hi, everyone. Please welcome Ariel Gabazon from Aztec, one of our lead sponsors. Ariel is the chief scientist at Aztec, and he'll be delivering a talk on FFTs on the projective line. Please give him a big round of applause.
Okay, thanks. So as a disclaimer, I sort of realized this last week, this is not a good topic to give a 30-minute talk on. The reason I thought it would be is I gave a 20-minute talk on this a few months ago, and I thought it went well. But after watching that talk 20 times to increase the number of views, I realized actually that it wasn't a good talk. It didn't really explain the subject. So with that disclaimer, let's start. I hope you'll find something interesting here. So let's start with a reminder of the classical FFT. We have some subgroup in our field of size that is a power of 2. And we want to evaluate some polynomial of degree smaller than n on this set. So we use the following recursive formula that I'm guessing most of you have seen in your life. We write f as, we decompose it to the even and odd coefficients. We can write f as f even of x squared plus x times f odd of x squared. And because the mapping going from x to x squared is a 2-to-1 mapping on S, right? Because if we look at all the squares in the set S, we'll get a set of half the size. Then this formula reduces these n evaluations of f to n over 2 evaluations of these two polynomials of degree n over 2. And we can continue like this because the set is of size of power of 2, and this gives us the classical FFT. But this requires n to be to divide p minus 1, where p is the field size, because otherwise we won't have such a subgroup S. So a question that people recently in Snark world, Snark land, have been very interested in is, can we work with n when n divides p plus 1 instead of p minus 1? Can we have a fast FFT? Why are people interested in this? Because they want to work with the simplest field possible in terms of its representation in binary form. And that's what's called a Mersenne prime, where the p is 2 to the k minus 1. So for example, everybody's working now with 2 to the 31 minus 1. And then obviously, in the case of a Mersenne prime, p plus 1 will have a large power of 2 inside of it. So that's the question the talk focuses on. Can you get a fast FFT when n divides p plus 1? And the central idea, one of them, is that really the main thing you need is a set with a cyclic operation on it. So again, looking at the classical FFT from that viewpoint, we have the map x goes to g times x. And this map sigma, x goes to g times x, it goes over s in a cycle, right? You start from any point in s, you apply sigma repeatedly, then you will go over all of s. And let's see how all the FFT can be sort of derived from sigma. So we can define tau to be sigma to the n over 2. So sigma applied n over 2 times. And you can check that in this case, tau will just be the mapping x goes to minus x. And just from the fact that sigma is a cycle, we get two things. So we get, first of all, that tau has order 2. Tau squared is like sigma to the n, so it's just the identity operation. And because of that, S will split into disjoint pairs, A tau of A. And now, right, a main component in these FFT algorithms is a 2-to-1 map. So we can define the mapping n of x to be x times tau of x. I call it n because it corresponds to the norm of a certain field extension, but that's not important to know. And now I claim that this n will always be a 2-to-1 map on S. Why? Because right, if you do n of A, that's A times tau of A. And if you do, because it's of order 2, then if you do n of tau of A, you'll get the same thing. So n gives us this 2-to-1 map. Right, so we got all of this just starting from some cyclic operation on the set S. So can we find, since we want to work with p plus 1, can we find a set of size p plus 1 with some cyclic operation sigma on it? And this naturally brings up what people call the projective line. So what's that? That's where we take our field f, think of it as points on a line, and add the point at infinity. So of course, this is a set of size p plus 1. And how are we going to operate on this set? We're going to look at fractional maps. We're going to look at the map going from x to 1 over ax plus b for some fixed a and b. And we want to think of this as an operation on p. So there's 2 points where you're a little unsure what to define. So for example, the point minus b over a, it's going to make the denominator 0, so 1 over 0. So let's say that sigma maps minus b over a to infinity. and we need to say what sigma of infinity is. Well, that's kind of like 1 over infinity, so we'll say that sigma of infinity is 0. Okay, so we defined the map sigma, and indeed you can look in the paper of Li and Xing and see that really there is some choice of A and B such that sigma will be a cycle over all of the projective line. So you might have been hearing the term circle Stark lately a lot. So a lot of times people look at the projective line as a circle in the plane. The way you do this is you draw a circle above the x-axis, and then to map the circle to the x to the line, to see where a point maps to, you draw a line between the north point of the circle to the point you want to map, see where it meets the x-axis, and that's the point that in the line that the point in the circle maps to. And then you ask, well, the point on the north, where does it map to on the line? Because it'll just be like drawing a tangent line to the circle that won't meet the line. So we say, well, that north point maps to infinity. Or you can alternatively just think of taking the x-axis and kind of bending it, and then sort of the point at infinity will map to the north point of the circle. Okay, but back to, so now we have, right? So we said all we need is a kind of a cyclic operation to get an FFT, so it's not going to totally work out. So let's see what happens. So let's try to proceed as before. So now instead of the mapping sigma x goes to g times x, we look at this fractional mapping. We know it goes over all the projective line as a cycle. And again, we can define tau just to be the map sigma to the n over 2. Apply sigma n over 2 times. And we know just from the fact that sigma is a cycle that whatever mapping this tau is, it will also divide p into disjoint pairs. Okay, now let's try to get the 2-to-1 map. So again, we can try to define n of x as x times tau of x, and try to say that it's 2-to-1 on p. But now we get into a problem because p is not a group, so a times tau of a is not defined. So here we kind of get stuck, and we need to go a little into algebraic geometry or algebraic function field theory, and go to a sort of different view of the point A. So this is where it gets a little more abstract or algebraic. So let's call K the field of rational functions over F. And now, given some point A in the field, let's match it with this set PA. So PA is all functions rational functions that are 0 on A. So P of A is called in algebraic geometry or the theory of algebraic function fields, it's called a place of K. And for those familiar with the term, so P of A it turns out to be the unique maximal ideal of the subring of elements that don't have a pole at A. So the reason we think we can think of P of A as like an algebraic representation of A is that, like, what can we do with A? We can evaluate functions at A. So this evaluation, you can do it in a more abstract way using PA. So let's see an example of that. So fix a polynomial f. We have to work with rational functions, but for simplicity, let's talk about a polynomial. Say we want to evaluate f at A. So we can write f, instead of in the regular monomial basis, in this basis of monomials of the form x minus a to the I instead of x to the I. And let's call this part, the non-constant part, let's call it G. So substituting A inside these equations, we can see that, well, G is going to be 0 on A, right? Because all these monomials, x minus a to the I, they're going to be 0 at A. So G is going to be 0 at A, which means it belongs by definition to this PA. And this constant C, right, if it's going to be equal to f of A, right? Because on the left-hand side, you have f of A, on the right-hand side, the only thing that is not zeroed out is this C. So in other words, we can evaluate f at A by taking f mod PA, by like writing f as some constant plus some element of PA. So that's why you can think of PA as like an algebraic representation of A. The nice thing about these places is that we also have a representation for the point at infinity. This is going to be the place P infinity, which is going to be all the functions f over g, where the degree of g is larger than the degree of f. And right, it makes sense that this is sort of the functions that are 0 at infinity. Since the denominator has larger degree, it's intuitively the functions that are 0 at infinity. Okay, so now we want to use this framework of places to sort of get this FFT to work with this fractional map and not get stuck, to get somehow this 2-to-1 map we need. But to exemplify the ideas more easily, I'm gonna work with a tau from the regular FFT. Let's just think of tau of x is minus x. So the first thing we need to think about is, right, this tau was a mapping from the field to the field, or say from the projective line to the projective line. We need to define it on these places. So how do we do that? Well, first, we can define tau as an operation on the field of rational functions. How? Just by sort of substitution. We have some rational function r of x. We're gonna change the inner x to minus x, and that's it. So tau of r of x is r of minus x. And now we need to say how to apply tau on a place. So right, a place is just this set of functions that is 0 on A. So we're just going to apply it element-wise. We're going to define tau on P of A as just the set of functions tau of R over all of R in PA. And the cool thing is that this acts like just the natural map x goes to minus x, right? Because this gives us all the functions r of minus x, where r of a is 0, because we're in PA. So those are exactly the functions that are 0 on minus a, so which is p minus a. Okay, so now we need to do two more steps to get our 2-to-1 map. The first thing, we're going to look a lot at subfields, at what's called Galois subfields. Specifically, we're going to look at the subfield of K that is fixed by tau. So all the elements are such that tau of R is simply R. And you can check that this is f of x squared, so all rational functions in x squared. For example, if we apply tau just on the function x squared, so what does this look like? It's changing the x to minus x, and then doing the squaring, so we get back to x squared. A lot of the theory of algebraic function fields is about how places, quote unquote, split in extensions. And we're going to see an example of that right now. So again, look at some A in the field and let B be A squared in the field, like the base field. And let's look at the place P prime B in this subfield x squared. What does it look like? So by definition, it's all rational functions R in x squared such that R of B is equal to 0. So for example, let's forget rational functions. What does a polynomial in P prime B look like? It's going to look, we can write it like this, like similar to before, as a combination of these x squared minus b to the I. And since R of B is 0, f of B is 0, there's no constant term. Okay, but now we can apply the well-known algebra equality. This is some combination of x plus a to the I times x minus a to the I. So definitely it's going to be 0 both on a and minus a. So in our terminology that we defined, it means that everything that is in P prime B is going to be also in PA, but also in P minus A. So we had this place of the subfield f of x squared, and when you go up to the field K, f of x, it's going to be contained in 2 separate places. So we say that the place splits into two places. By the way, and I think this is a good time for, can I ask for questions? Yeah, this might be a good time for questions. We're pretty close to the end, but yeah, I think it might be a good point if there are any questions. think you got one over there.
Why do both terms x plus a and x minus a have to be 0 and not only one of them?
Well, if you have something that is a combination of x squared minus b, so it's going to be, right, a combination of x plus a times x minus a. So that implies that it's 0 both on a and minus. Because it's a combination of those, it's going to be 0 both on a and minus a. If you're a combination of things that look like x plus a times x minus a, then I think you have to be 0 both on a and minus a.
Thank you.
Okay, let's continue. We're pretty close to the end. We can. Okay, so now let's try to tie it together. So our goal was to define this 2-to-1 map N. So now a slight sort of formal change. If before we were talking about the projective line, we're going to think of P as all the places corresponding to the projective line. And as before, we know that sigma goes over P as a cycle. We can define tau to be sigma to the n over 2. And we know that P will split into disjoint pairs, P tau of P. And now we come to the sort of the punchline. So how do we define a 2-to-1 map? So let K prime be the subfield of K of elements fixed by tau. So it won't be this, for whatever tau we're going to get here, it's not going to be this field f of x squared. It's going to be some maybe other slightly more complicated field. And now define n of p. So we're going to know, I mean, I haven't gotten into this, that every place of K prime is going to split into exactly 2 places of K. So we're just going to define n of p to be the place of K prime that splits into p and tau of p in K. And okay, so that's a basic idea. For more details, I recommend the paper. And for a more elementary approach that ends up actually having better final FFT constants, I recommend looking at the Circle-Stark paper. Yeah, so thank you.
Thank you, Ariel. And any final questions from the audience? Okay, thank you so much, Ariel. And once again, a big thank you to our sponsors, Aztec. Next up is Emmanuel Ragnoli from Provably AI. And he'll be delivering a talk on verifiable analytics with verifiable SQL. Please give a big round of applause for Emmanuel's talk.
Thank you. Hello, everybody. My name is Emmanuel. Thank you, Marek, Oreste, the organizers, etc., for inviting me and my colleagues. Big disclaimer, there is no maths in this talk. Okay, if you expect something like Ariel did, you can go. because I'm actually going to start with a question, and the question is to you. So it's episode 3, season 6 of Rick and Morty. Who does not know Rick and Morty? So the title of that episode is Rest and Relaxation. So the two protagonists goes off onto a 6 days adventure, and they come back and they say, we need a holiday. Okay, and then some other stuff happens, etc., etc. But why am I saying this? Because in this journey that we did with Probably, we kind of went off through the same, more or less like any startup. So every day you die, every day you live, there are a lot of heart attacks, a lot of ups and downs, and etc., etc. And that made me think, actually, instead of giving a proper technical talk, I'm actually tell you a story. And a story that starts with once upon a time, and a product is a technology is a story, and this story actually starts in 2006. And it starts in the corridors of Hewlett-Packard in Palo Alto, California. One of the scientists, cryptographers in HP was Stuart Haber. And in a famous paper that was titled Privacy Preserving Verification of Aggregated Queries on Outsourced Databases, Haber and co-authors wrote, the scope of this work is on how to verify outsourced data and computation, including the verification of both correctness and completeness of relational database queries, such as select, project, union. We give protocols for privacy-preserving verification of aggregate queries, including sum, max, mean, count, average, and median. A little bit later, in 2007, we change corridors. From the corridors of HP, we actually go to the supermarket corridors of Tesco in the United Kingdom. Another mathematician, Clive Hamby, was basically the architect of the first Tesco loyalty card program. Clive understood that all the data that they could harness through the loyalty program could actually become a new source of information, insights, for what would become then one of the first marketing-driven analytics department. And he actually came to create the concept that we all use today, that is data is the new oil. The concept was then further precised, tuned by Michael Palmer, that said, yes, data is the new oil, but without it, we cannot do anything. We really need refineries. And the story goes further till a report of IDC that estimated that what is called the global data sphere, that is basically how much data we collect, use, etc., and how can we estimate that dimension to be by 2025, they came up with the conclusion that from 33 zettabytes in 2018, we would reach a dimension of 175 to 200 zettabytes in 2025. 1 zettabyte is 1 billion of terabytes. More interesting than that is that if we take all the type of data in the data sphere, so from Internet of Things to web data to marketing data, etc., the healthcare data are actually the one that are gonna outpace any other category in the industry by 2025. estimated to be more or less 30%. Why is this important? It's important because with all the new privacy regulations, laws, etc., that we as a society have implemented, we're actually gonna have 30% of the data sphere that is subject to very strong privacy guarantees. So, a product, again, is a technology. A technology is a story. And the story is not a spaceship, it's a time machine. It goes back and forward. It takes us to a place where we want to go again. In fact, as a techno-societal set of forces that sort of bind us together, we live in this type of dichotomy in which we have this and we live in this huge data sphere, but somehow we still demand, require, wish to live with privacy guarantees that are probably more adopted to a society that was born in the 80s or the 90s. Recently, I don't remember whom, unfortunately, made the comparison that if we were to map the cyberspace into a physical space, the wishes for privacy that we have, not the practices, but the wishes, are that we would basically want to be a person that walks in a very crowded street and is completely covered in a burqa, such that basically, even if I were to meet a friend on the street, he would actually not recognize me. As I said, a story is not a spaceship, and it's not a flying machine either. And this story actually brings us back to a machine. So, and this story is actually personally related to some of us, the co-founders of Probably. This story goes back to 2016. So, other corridor at the time were the corridors of IBM Research and IBM Consulting, and the corridors of academia as well. Myself and Shyam, my co-founder, we had basically all the data that we wanted from an electric vehicle. And the goal and what we were trying to do was, what do we do with that? We can apply all the algorithms that we want. We want to create a smarter car. We want to make inferences and insights or allow the owner of the electrical vehicle to have the same. Similarly, in the corridor of academia, one of other colleagues and co-founders were starting to dabbling with the idea of I have a database and I want to extract insights, and how do I do that without violating privacy? And going a little bit further, we are seeing more and more the same needs happening further up in similar contexts. So we have blockchains or Web3 that is started to require to operate more and more off-chain data that sometimes are personal, sometimes comes through TLS and notaries, sometimes are very much needed for regulatory or other financial purposes to create DeFi applications, for example, in personalized lending, or to bring the concept to the more modern fields of artificial intelligence, large language models that need more and more proprietary data to create smarter LLMs. So what are we trying to do actually? So we are trying to do something that is called collaborative computing. And we are trying to enhance that with what we define as data ecosystems that are much more than the existing distributed physical networks or data curation networks. Because it's not enough just to collect and curate data, but there is actually the need to structure them in order to extract insights and to somehow create relationships, relational insights. The moral, as in any story, is that we are allowing insights from sensitive big data. And the problem is, and note that I have introduced that at page 11, already after 12 minutes for the first time, we need to understand if we can scale zero-knowledge techniques for efficient analytics on big data. To do that, we need what is called analytics. It's not enough just to use ZKPs to shield transactions or to apply them to Monero styles of cryptocurrencies where addresses are obfuscated, etc., etc. Analytics is very different. Analytics, when I work in an analytics department in a company, Web2, etc., etc., I actually need to do much more. I actually need to produce these type of graphs. And the primitives for the construction of these are actually statistics, queries, etc., etc. So how do you do that with the current set of privacy-preserving technologies? The old way was I dump all the data. Excuse me a second. I dump all the data in a database, and I allow some departments in my company to do SQL queries on that database. But I do it by myself, basically. It's the same security perimeter. There is no distribution. There is no proofing, etc., etc. What we call the smarter new ways is that you really try to harness, or we really try to harness, the data coming from different sources, from different databases, to actually create collaborations. Regardless of the incentives that we put underneath. So, for example, in Web3, what some of the assets held off-chain in terms of artificial intelligence and personal recommendations. So, can I get an average of the number of steps from other users from where till such then I can understand was it the benchmark for my health, etc., etc. Or when it comes to business ecosystems, can I pay for gaining insights from your data and not necessarily only mine? So this big market that we try to address with privacy-enhancing technologies is booming, but there are still a lot of challenges to solve. Typically, what is the process that I do if I want to compute analytics in conjunction with somebody else? So if I am company A and you are company B, and we both have an instance of Snowflake, for example, we first put in touch our legal departments that write a very strong contract that will penalize each of us, etc., etc., if data are leaked. Then once the contract is signed, etc., etc., we both go into Snowflakes. My data set is masked bar some of the rows and columns. You, as the insight seeker, the other company, can access those rows, run SQL, some average, etc., etc. But the point is that even with that level of data masking, the rows, columns that you want to access to are actually open to you, and you can copy, access them, etc., etc. And this is what we call the basic privacy preserving technologies. If we want to go to something much more advanced, like fully homomorphic encryption or multi-party computation, well, it's not so easy out there, especially in Web 2. It's true that Web 3 is adopting more and more, but Web 2 not so much. The analytic market has not really opened itself to this type of techniques because they are too complex and from a certain point of view have not proven themselves. They are not mature enough. And they are also not very well performant. So what we really want to do is analytics under privacy for big data, and we want to solve trust and verifiability for this type of data sets. So in this long journey that started in conception many years ago, that went through some iterations, but that really started to be focused last November, we came up and we designed what is called Probably. Probably, it's a verifiable analytics middleware, and it works in this way. So if you are a data owner, and you are a regular database, a relational one, or decentralized databases, or even a privacy-focused blockchain, you can integrate them with Probably. An insight seeker, so a partner or somebody else, is going to submit a query. For example, what is the age and the average income subject to country, etc., etc. Typical SQL approach, nothing more. What the insight seeker gets back is an answer to the query. Now note that the insight seeker never accessed the health data or the financial data or the distributed finance data, and he gets back a proof as well, a zero knowledge proof. That the query was done correctly, computed correctly on the corrected data. The computation is done locally, and the data is never revealed or seen. We have shipped these just a few weeks ago. What is it exactly, and which type of proofs do we give? So we provide aggregation queries together with verifiable proof, which allow the insight seeker to trust the results with the 3 different types of proofs. Correctness, so the query answer has been correctly computed. Completeness, all and only the records satisfying the filter condition of the query contribute to the answer. And the membership, so all the values which contribute to compute the query's results belong to the database columns specified in the query. And how does it work? We haven't really done any science fiction. We tried intentionally to be extremely simple in 2 ways. First, we wanted to adopt something that was old but had survived the test of time. So, for example, intentionally, we did not go for Nova. Not because we discriminate against Nova, but because it's much younger than other techniques out there. In terms of this slide and software engineering, we actually went for a design concept that is really in the ABC 101, etc., of DevOps stuff that, for example, if you are into patents, etc., you would never patent because it doesn't make any sense. It's what a developer does every day. So what did we do? It's a domain-specific language, a subset of SQL that allows analytical operation, already existing. It's a parser that makes sure that the queries are correctly formed and are compatible with the features. It's a data fetcher that interfaces with the underlying relational database in terms of ZKPs and zero knowledge. It is a prover that connects the customer database and computes the result and the proof. And it has a verifier. Again, verifies the proofs, etc. The proofs are stored in a simple storage. We have an REST API. And more importantly, especially for this audience, apologies, these are not supposed to be there here. The building blocks are 3. And as I said, the design choice that drove, the design requirements that drove the choice of the protocols were based on simplicity, openness in terms of open architecture and open software, and also something that was, and number 3, something that was old enough, at least 10 years, well, a little bit bulletproof, sorry, is 2016, if I remember. But basically that had been out there and that was attacked, etc., etc. But also the realization that we could not really go for a snark type of architecture because databases, MySQL, etc., etc., are a little bit too complicated for snark, for circuits, etc., etc. While a protocol that is based on inner products and compute range proofs, like bullet proofs, could basically sustain queries done on MySQL, for example, while being at the same time performant enough. So, as I already mentioned a few times, we implemented Bulletproof based on a very well-known, famous repository that is the leading repository out there, Dalek. And we used Bulletproof for the range proofs. Similarly, we put in Pedersen commitments because they are addictively homomorphic, they are unconditionally hiding, and computationally binding. And we used them as a basis to compute the correctness and the completeness proofs. And a non-interactive Chaum-Pedersen proof that comes again from a very old paper of Chaum. I don't remember when that was. I think that's even 1998, if I remember correctly, but maybe I'm wrong. That is basically used to provide a zero-knowledge equality proof. This is the roadmap that we have implemented and that we are following. We released our alpha version in August, again, based on Bulletproof, Pedersen, and Verkle trees. We support SQL, we support Postgres as a database. The aggregations that we have at the moment are sum and count. And at the moment, there is a front end for data owners with multi-data source support. In October, we augment that with new aggregations that are average, median, standard deviation, and the variance. We support smaller than, bigger than, smaller or equal, bigger or equal, not equal is null, not null. And with the beta, we also come out with a front end for the insight seekers, so the other side of the collaboration. While this is already all done and it's in production and at the moment being tested, we have started to work on the next phase. While we worked on alpha and beta, and we knew that already, we always realized that there are, while the trinity of Bulletproof, Peterson, and Chaum and Verkel 3 works very well for certain dimensions in terms of rows in the databases, 100,000 to 1 million. If we really want to scale up in a performant way, we need to start to tweak the protocol. So we started to work on an implementation inspired by Tavloid. Tavloid is a protocol that was proposed by Matteo Campanelli at the time in Protocol Labs, now in Matter Labs, that uses vector commitments and set accumulators. We are going to support SQL and Python. The database horizon is bigger, so MySQL, Postgres, and BigQuery. And it comes out that actually that some of the toughest aggregations are actually grouped by and join. So those will come in towards the middle of 2025. I really don't have very much time left, it tells me here. So I'm going to skip through the use cases, also because I think there are two ways to end up stories. One way is saying, and I think it goes something like, they all lived happily forever after, or something like that. But I think my favorite one is actually Michael Ende, The Never-Ending Story, that says, but this is another story and shall be continued another time. And because at 6 o'clock in 1 hour, we actually have a workshop on this, in which we actually go through more details in terms of the techniques, the maths, but we actually as well showcase the product, how it works, and actually you can actually use it. So I invite you, if I didn't bore you too much, to actually move over there then. Thank you.
Thank you, Emmanuel. Does anyone in the audience have any questions? Okay, looks like no questions. Thank you so much, Emmanuel, and thank you once again for to Provably for sponsoring Verifiable Summit. And now it's time for a networking break in the room upstairs, and that's going to last 30 minutes, and then we'll kick off a few lightning talks. So please make your way back up to the main area where you can grab some snacks, coffee, and tea. Thank you. please start making your way from the networking room to the main stage, side stage, or workshop room. Talks are about to restart. On the main stage, we have a lightning talk from Mihail Zions from Nethermind on Mova improving Nova folding scheme. Everyone, please start making your way to the rooms, depending on which talk you want to attend. One minute left till talks restart. Please make your way to the main stage, side stage, or workshop room based on which talk you want to attend. Next, on the main stage, we have Mihail Zions from Nethermind talking on Mova, improving Nova folding scheme. Volunteers, please start ushering attendees to one of the stages, main stage, workshop room, or side stage. Talks are about to begin. Attendees, please make your way to the main stage, workshop room, or side stage. Talks are about to begin. Last call for attendees, please make your way to the main stage, side stage, or workshop room. Talks are about to begin. Everyone, please welcome Mihail Zions from Nethermind. He'll be giving a talk on Mova, improving Nova folding scheme. Please give a warm round of applause.
Thank you. So thanks for introduction. Yeah, let me talk about MOVA and like folding without commitment to errors. So maybe let me begin with why folding and what folding is. So basically, when we talk about the zero-knowledge proofs, so we are talking about proving particular relations. And this relation takes usually two inputs, one being some statement, here X, and another being witness. In zero-knowledge proofs, statement is, statement is public and witness is usually private. This is the value that we want to hide from the verifier. Right. So in folding scheme, we have our usual suspects, prover and verifier. So in this case, prover has as input two instance witness pairs, and similarly, the verifier has two instances to be verified. So what prover wants to show is that both instances belongs to some relation R. So in folding scheme, prover and verifier interact to create some sort of joint instance witness pair, here X3, W3, with a very particular property, namely if this if relation on X3, W3 hold, then relation on X1, W1 and X2, W2 hold as well, right? So we somehow reduce two instances into one. Okay, so why do we care about folding? So we have our two relations, X1, W1, X2, W2. We fold, we come up to X3, W3. So we can reduce a task of proving two instance witness pairs into proving one instance witness pair, okay? So you can imagine that if you have like a prover that was tasked to prove like both X1 and X2, at the end of the day, the prover needs to prove something much smaller, being like X3, W3. I mean, it's not smaller than each of the X1 and X2, but it's smaller than proving like both separately. So here we need some design principle, namely the folding itself needs to be relatively cheap. Like it needs to be cheaper than like proving the instance witness. And one of applications for proving are so-called continuations. So you can imagine that you have like a super big computation. Think about like, I don't know, like ZKVM execution. So what you can actually do is you can divide this very big relation, this computation, into much smaller chunks and fold all these smaller chunks, all these instances, into a single small chunk, and then prove this small relation instead of proving this very large relation. Another use case is like efficient incrementally verified computation of proof carrying data. Okay, so before I go into MOVA, let me talk about NOVA. So this is like, I believe, first folding scheme that became very popular thanks to the work of Kutapalli, Sethi, Tsealia. In NOVA, the authors defined something called committed relaxed R1CS relation, which is roughly the relation as follows. Maybe I can, yeah. So on the left-hand side, we have our instance and witness, commitment to instance and witness that is denoted as a Z with bar. In general, like throughout this talk, I will refer to committed values as values with bars. And we have some error term E with also bar. So here you see like our well-known like R1CS relation, but with some twist. So A, B, and C are matrices that describe our computation, our circuit. Z is our witness, so like the evaluation of the circuit gates, and E is the error that comes from folding, right? And because ABC denote the computation we are doing, our circuit, these are public matrices. Importantly, we have also access to the commitment, to the witness and the error. Okay, so let's take a look at NOVA from 5,000 feet. So we have two relations, two relaxed committed R1CS relations. So we have Z1 bar, E1 bar. So this is like the public part. Z1, E1 is the private part. We have Z2, E2 bar with bars, the public part, and Z2 and E2 as a private part. Okay, and this is given to the prover, of course, like the both public and private part. Verifier learns only the public part. So what prover does is it commits to a vector T that is like a commitment to so-called cross terms. This is like a big part of NOVA. And verifier responds with some challenge alpha, and P and V jointly compute this folded relation Z3, E3 with bars on their own. Okay, so why they can compute this Z3 bar, E3 bar, it's because like Z3 and E3 are linear combinations of Z1, Z2, E1, E2, and T. So here, this alpha Zi, alpha Z2 are values that are derived from this alpha here. All right, and they are like publicly known because the alpha that V sent is known. Okay, so how we compute the commitment to Z3 and commitment to E3. And here is where we are using the homomorphic property of the commitment scheme. And homomorphic property here means that if I have a commitment to some value A and I have commitment to a value B, then when I add these commitments, I have a commitment to value A plus B. And similarly, we can use these coefficients alpha Z1, alpha Z2, etc., and commitments to Z1, Z2, E1, T, E2 that I know to compute the commitments Z3 and E3. Okay, so let's talk about cost. So yeah, the vector T is called cross term, and committing to T is like a bottleneck of this scheme in many cases, in many like real life cases. So and this is because T is filled with random field elements. And so like each entry has like a logarithm of the size of the field bits. And this is actually committing to such vectors is actually quite expensive. So we need like roughly like 2 to the 8 times T field operations, T like size of the vector field operations. And this is like a dominant cost. So to provide some concrete benchmarks, so we looked at Pedersen commitment over Pallas curve and the commitment to T. Like here we have like the size of the witness, commitment to T. It also depends, of course, on the size of the witness. And like in NOVA, folding instance of size to the 16 like took roughly half of a second. And like 88% of this time was the part where we had to commit to T. Okay, so now let me talk about MOVA. So MOVA allows to fold instances without committing to E or to T. Okay, so first question is, why does P need to commit to T? So the only reason why P needs to commit to T is like it allows the verifier to compute the commitment to E3, and this is because, like as we said before, there's this E3 is like LC, like here stands for linear combination. So E3 is linear combination of E1 bar, T bar, E2 bar. Okay, by what if V needs to compute E3 bar? So So actually, this if3 bar is a part of an instance in R, right? So that was our relation. But do we really need if3 bar in this relation? So maybe not. Maybe not, because like as we observed, the commitment to E, to this error term is actually redundant. And this is because if3 is implicitly committed to by commitment to Z3 bar. And this holds from this equation below, right? So if we have like public values A, B, C, well, and you, sorry for confusion, you shouldn't be here because like we have this simplified version of relaxed R1CS instance. And we have Z3, then like this if3 is like, is known, right? It's like, we can solve this equation. So the question is like, can we actually just delete E from the definition of R? And this is, no, not really. Like there are some technical details why we cannot do that. And like to give like some overview of the technical details, when we commit, when we reduce R1CS instance to commit relaxed R1CS, we actually need to beat E to be 0. And in Nova, it's done by setting the commitment to E to be a commitment to 0. And this is why we need to commit to E in R. But actually, we realized that we can do some trick and replace commitment to E by an evaluation of multilinear extension of E at a random point. So what we do is that we introduce relation R prime that has some additional values V and R. And instead committing to E, we have this multilinear extension of E at some random point R, and the claim is that this multilinear extension gives a value V. Okay, now we require prover to send this multilinear extension instead of sending the commitment to T. We also do some randomization of the point R and each folding step. Okay, so how MOVA look like? So this is our relation. We have prover, verifier. Prover has like the pair of relations. Verifier has like, sorry, pair of instances. Verifier has also like a pair of instances. Here we assume that R1 or R2 equals R, but this is like a technicality. So the first thing, like the prover sends, is this multilinear extension of T at R, and V replies with some challenge alpha, and this way we get like a new folded relation. And here the trick is that, okay, so as previously, like Z3 is just like linear combination of Z1, Z2. E3 is linear combination of E1, T, E2. And Z3 is like linear, Z3 bar is a linear combination of Z1 bar and Z2 bar. And actually, like this multilinear extension of E3 over R can be computed as a linear combination of these multilinear extensions that we already know. Okay, so regarding performance improvements, compared to Nova, we observed over 6-time improvement for instances of size like 2 to the 16. For 2 to the 20, actually, like the improvement is a bit smaller. This comes from the fact that Nova actually like performs a bit better with higher instances. So the setting we did that was like the R1CS witness contained only like small entries. ABC were identity matrices, and like MOVA's verifier cost is similar to Hypernova verifier, but we have like constant number of rounds, and Hypernova has logarithmic number of rounds. Yes, so here we can see like a matrix of like this performance of the scheme. So for Nova, like we see that prover like has like less smaller number of like field operations, but we also need to commit to T, and that what makes Nova much more much less efficient. Okay, and one additional thing here is that in our work we try to answer question like, can we have like efficient R1CS folding scheme where the prover commits to only to witness and the number of rounds for verifier is constant, and we thought that we were first to answer this question like affirmatively, but actually like Ariel's Gabi's own work on ProtoGalaxy was also like answered this question positively, and like from some perspective that the MOVA is some sort of specialization of ProtoGalaxy scheme. Okay, thanks a lot. I'm happy to take questions if we have time. Feel free to connect using this QR code.
Let's take one question and then move on to the last talk. Any questions from anyone in the audience? Okay. Thank you so much, Michał. Great talk, and we appreciate you coming. Thank you so much. Next up is Jünger from Tycho, speaking about Tycho's approach to multi-proofs. Please give him a big round of applause.
Thank you for a kind intro. Oh yeah, hey everyone. I hope everyone's okay. I will talk about multi-proof system today. I'm Jünger as a particle physicist, but currently doing research and technical writing stuff at Tycho Labs. This presentation prepared with the contribution of our ZK engineer, Cecilia. Okay. 34,469 lines of code won't bug free a long time. Vitalik said this about ZK EVM, the privacy and scaling exploration. So yeah, this is let's build from the scratch to the foundation level. We are building very complex stuff. This stuff is a big circuits like ZK EVM to prove EVM, to all of the execution on the EVM to prove in a circuit. These circuits includes very complex gates, wires, and arithmetization. So we don't want to trust the code because it's not mature yet. I mean, in theory and implementation, not only in implementation. So yeah, currently, most of rollups are centralized because the security issue. You know, we know this code is very complex. We don't want to throw away to make it open source, to make it verifiable. The centralized rollups can protect the chain from the malicious attacks. This is the main issue on the centralized rollups. And also immaturity of ZK. This is a very immature yet. So I mean, still implementation side and also theory part. The proofs can be broken in context of soundness and completeness. This means a proof can valid, but verifier cannot convince about that. So we have to prove the block in just one proof. There might be only one proof, but it can be different proofs, so we don't want it. It's impossible, I mean, in theory. The end game of L1 is snarkify everything, we can say. But this snarkify everything stuff, it will be absolutely through multi-clients. Multi-clients, when we say there is Rust Ethereum, and there is Geth, Go Ethereum, we have to distribute the risk through different type of clients. Yeah, it was about why everyone needs multi-proof. This is why we need multi-proofs as a Tyco. A Tyco is a base rollup. That means everyone can propose a block. It's fully permissionless. But this permissionless stuff, it's coming as a cost, permissionless attacks. Centralized rollups may tolerate a certain risk, but Tyco cannot because we embraced the decentralized from day one idea. So we can't fully trust on the same prover. So we wanted to distribute a lot. How? What we say multi-proof, but how? The multi-prover can be, as I say, different implementation by different teams. So one client has a bug, but the other type of clients cannot. So also we can distribute the proofs. It can be validity or fraud proofs. And also we distribute the validity proof as ZK and SGX. We also use SGX. And also we can use Snark and Stark. Our roadmap and our idea is, as I said, we can't trust the only prover because it's permissionless attack, as I said. So we embrace the idea to prove every block with SGX. If someone can have idea, this proof can be wrong. So I require and I demand ZK proof. So if the proof is wrong, I mean the SGX proof is wrong, so you can request a ZK proof and the SGX prover will be slashed. And also we have guardian proof after all of that. So yeah, Ryko, our multi-proofs, is Ethereum and Tyco block prover, is our proof supply chain. In our way, multi-proofs, it's multi-clients compiled into different multi-snarks. Our provers, I mean Ryko, includes different type of ZK VMs. Previously we contributed a lot to PCE ZK EVM, but the specific implementation of circuits, I mean ZK EVM is an implementation of just EVM. So it's not so efficient. Thanks to the ZK VMs, we can verify all of the codes, all of the Rust codes, and also in other languages, like thanks to the LLM. Currently, we have SP1, RISC-0, and SGX, but we ongoing effort to implement Powder Labs, Jolt, and also Amazon Nitro and TDX as a different type of SGX proofs. The pipeline is basically like that. We taking the proofs from different execution clients and turning into assembly languages. You can see here more. This is not implementation, this is in theory, like an example. So, for example, we have Geth and Reth, and we can turn to the assembly languages like RISC-V and WASM. So we have already 4 types of proofs without implementing the ZK stuff. And also the arithmetization through Air, Peel, Plonk, it can be anything. We can turn it into the Snarks and Starks. Currently, most of ZK VMs support Stars. We prove every block with SGX currently because we are base rollup. We have to push blobs every 12 seconds because the sequencing role is fully belong to Ethereum L1. So we have compatibility with Ethereum thanks to block time. But if you want to prove every blocks with DK, if you're base rollup, you'll be fucked up because it's not efficient. It's not efficient, we still believe SGX is a reliable guardian, but if you have a fallback. So we don't want to trust fully on SGX because it's not open source and there is no proof of fabrication. So we don't know how it's built. So we don't want to rely fully on SGX, but still it's a reliable guardian for us. So we use Gramine OS to wrap the guests on the SGX enclave. So we are taking different proofs, but for example, ZKVM and TEE, we have to standardize all of the inputs. It can be SGX, it can be ZKVM, So you can see at the diagram, so you can request proof from the host with different guests, and the host can generate a proof for you. Future plans, thanks to our pipeline, we want to implement all of RISC-V-based ZK VMs and also WASM-based ZK VMs, like Fluent or something. Currently, all blocks are proven by SGX, but as I said, we don't want to fully trust on SGX. Our future plan is prove every blocks with ZK, but it will be gradually increased because still, I mean, it's not fully efficient right now. It can be maybe 1 block per 1,000 block will be proved by ZK. And also we want to adding direct data retrieval from the REST to skip RPC overhead. So thanks, that's it. Do you have any questions? Seems like no. Thank you again.
Thank you very much, Junger. Big round of applause one more time. Next up, we have Vanishri Rao, and she'll be presenting on the next frontier of cryptography, witness encryption. Please give a round of applause for Vanishri.
All right. Hello, everybody. My name is Vanishri Rao, and a little bit of quick introduction is I am the founder of Firma. Firma is a universal proof generation layer that is designed to generate proofs for any proof system in a cheap, performant, and reliable manner. And it functions as a marketplace where the supply side consists of any kinds of machines, GPUs, FPGAs, VPUs, etc. And for the demand, we can generate proofs for any situation where ZK is used. So that's what we are building. If you are a ZK project, there is a huge possibility that we can add value. Please reach out or head over to firma.xyz, and there is a form there that you can fill. And let's see. And a little bit of background about myself is prior to founding Firma, I have been working on ZK and cryptography in general for over 15 years on projects such as Mina, and my PhD was in cryptography at UCLA. That's a little bit about me. And now on to our topic at hand, right? Witness encryption. Let's begin by understanding why we should care about witness encryption. And the amazing thing about our industry is that we have a tendency to take these diamonds in the rough and polish the heck out of them, right? One example is ZK. When our industry started working on ZK, it was not practical in general, right? Look where we have gotten it, and look where we are taking it, right? And we are starting to do the same thing with fully homomorphic encryption. A natural question is, what's next? Or what makes a cryptographic primitive, a cryptographic tool, a great candidate for our industry to embrace like this? And my thinking is that it comes down to these three things. One is that it has to be extremely powerfully useful, if efficient. And it is currently not efficient. And then the third thing is that the value offering of this tool has to align with the crypto ethos, right? One candidate for one candidate that satisfies all these things, I think, is witness encryption. So as we will talk now, as we will discuss further, one thing you will realize is that witness encryption is actually really powerful in that it'll help us achieve truly trustless systems in a way that we were not able to do earlier. And this is why it is so corely aligned with what we believe in our space. This is the agenda for the rest of the talk. So we'll first see what witness encryption really is. Then we'll talk about a few applications. And then we will infer this thing that I just mentioned, that from these applications, from understanding what witness encryption is, infer that witness encryption is a great tool for us to build truly trustless systems. And finally, we'll look at the current state of the art of witness encryption and try to predict the trajectory, the future trajectory of witness encryption. So, okay, and this talk will be short. So later, I'm hoping to keep this as intuitive as possible, and hoping to have enough time at the end where we can have a discussion. So what is witness encryption? I just wrote a takeaway there, but before that, let's try to understand witness encryption from something that is more popular, public key encryption. Let's begin with the notion of encryption. Witness encryption, of course, is a form of encryption. That is very clear. So it helps us hide message so that only qualified people can open it. That is clear, right? What is public key encryption? Public key encryption is a method where we encrypt a message to a public key so that only people who have access to the corresponding private key can open and read that message, right? That is public key encryption, right? So what is witness encryption? In witness encryption, instead of encrypting to a public key, to somebody's public key, we are encrypting to a puzzle, right? You encrypt to a puzzle. And whoever knows the solution to that puzzle can open up and read the messages, right? That is witness encryption. And to formalize the notion of puzzle, in formalism, we say that you encrypt to a statement, and whoever has the witness to that statement can decrypt the ciphertexts, right? And here, just like in ZK also you prove a statement where the prover has access to the witness, and the verifier can verify with just the proof and the statement. So it's all, everything is all, we start with, it's a similar notion. It's a similar notion of puzzles where there are statements and witnesses, right? So this is what witness encryption is. Feel free to stop me in the middle. Just raise your hands, and I'm happy to chat in the middle because we have plenty time. Okay, so here is an example application of witness encryption, right? I find this really cool because so try to think about how we could have achieved this in the absence of witness encryption as we describe this, right? You'll realize that it is really hard to achieve something like this in the absence of witness encryption, which tells us the power of witness encryption. So the example goes like this. Let's say you want to send your keys to your NFTs to your great-grandchildren who are not born yet. What would you do? If you keep a network of TEs and secret share your key, there is some trust. The trust that people won't break TEs. Even if they break TEs, people don't collude and get your secret. Imagine this is worth $1 billion and it takes $2 million to break a TE. Of course, they'll put $2 million to break it. and collude and get your secret key. So there is some trust, right? Can we build a truly trustless system? And the way we can build it is through witness encryption. And here is what you would do, right? You would encrypt your secret key to the statement that I am the great-grandchild of Alice. And the witness is some proof that you're a great-grandchild of Alice, and if you have that proof, you can open it and get the secret. Otherwise, you cannot open it. You can leave this ciphertext out in the open, and without the proof, nobody can open it. So there is no trust you're placing on some system. It's a truly trustless system. You don't even, it is very hard to, I don't know of any other way to store a secret in a smart contract, for example. If you want something, some access control to be done on a smart contract, it's really, really hard. This is the way to do it. Here, this is one example. A similar example, while we stay on this slide, is let's say you're a whistleblower, right? And you want to get to the chief detective of an intelligence agency, get the information to that person. You don't know who that person is. You don't know how that intelligence agency operates. You don't want it to get to another person in that intelligence agency. So you can encrypt. Here's the thing. You don't need to know the identity of the recipient when you're encrypting. This is the cool part about witness encryption. You don't need to know who that person is. You only need to know some qualifying information that person has that others don't have, and you encrypt to that. That's another kind of an example. Okay, and I have one more example. There are a lot more examples one can think about, but here is somewhat of a different example. So we, in our industry, started building private protocols like Zcash, and there was a pushback from the powers that exist, and our industry softened our stance and started building, I think it's the right thing to do, started building compliant privacy protocols. Labyrinth is one example. I think it's a very cool project. Labyrinth is building compliant privacy, right? With witness encryption, you can further soften and make it more amenable for the powers that exist by building compliant privacy with auditability, right? When you think about compliant privacy protocols, something that is private, right? That powers, the powers that exist, they don't like it. They want to be able to get into things when they need to. Even if somebody is complying within the protocol, they may do things off-chain because of which people need to get into the secret information, and compliant privacy protocols don't allow that. But witness encryption can help you get there too by encrypting the private parts using witness encryption to the statement that you have a court order to open up to decrypt, right? Thereby you can build compliant privacy with auditability. Here, this is just another example. Okay, so these are a couple of examples, and what we learn from examples like this is that a realization, a reinforcement of our ethos. We are not here to build decentralized systems versus centralized systems. This is a higher. This is not the first order core goal of our industry. The first order core goal is building truly trustless systems, and in the absence of tools like witness encryption, we resort to mechanisms like decentralized systems. where there is some level of trust. You can remove that level of trust with something like witness encryption, and witness encryption clearly helps us build truly trustless systems. And this, I think, is my last slide. Where are we and where we are headed? I want to compare this trajectory with the trajectory of ZK. Very, very likely it is going to take the trajectory of ZK. So let's first, at a very high level, look at the trajectory of ZK. ZK, of course, started even before crypto existed. There was this long, active line of research in the academia before we started working on it, and we started building these generic systems that were inefficient, right? These interactive protocols that were inefficient, and then we started building specific efficient protocols for specific computations that you wanted to prove, and then blockchain started noticing ZK, and through projects like Zcash, we built specific kind of efficient, almost efficient ZK. And then we realized that, okay, there is more attention. We need to help people build these specific efficient ZK. And tooling came like Circom, Noir, and then we realized the pains of building even through Noir and all these cool tools, because people still had to learn these tools to build with these tools, and there came ZKVMs, tooling for generic. And that has catapulted the adoption of ZK, and we are we are on the way to have a huge amount of adoption through that, with a few things here and there that are still that still need to be done for absolute mass adoption. And I also wrote another item at the very end. Will we switch to something specific? So we went from generic to specific and specific to generic. Will we go to specific? There's a tweet debate. There's a debate on X recently. I am of this thesis that for projects that become so mature to a level that they don't have to worry about the bootstrap constraints of a project, the time to market, the cost of engineering, where the engineering team is building specific circuits, when those constraints go away, then I think it makes sense for those projects to reconsider the ZK stack. And there might be room, space for specific. Anyway, that's just a side note. That's in general the trajectory of ZK, right? And for witness encryption, we started off in academia, of course, and we had the first feasibility results, I think about a little over 10 years ago. I think just about 10 years ago, 2013. And now we have realized that it is really, really hard to build witness encryptions that are generic, especially the starting points, the enabling points, the ingredients to build witness encryptions themselves were really, really hard to manage, like indistinguishability, obfuscation. And we didn't want to take that route we didn't want to take that route to achieve what we could achieve with witness encryptions. So people started looking at witness encryption for specific languages, for specific set of statements, right? The two that I've listed here are witness encryption for signatures. If you have signatures to certain things, then you can decrypt, right? Or if you or for functional commitments, if you have if you have openings to functional commitments, then you can open or decrypt those ciphertexts. This is where we are, it seems. And if you are to see where witness encryption is, the trajectory that witness encryption will take, it is very likely the trajectory that ZK has had, and because it's such a natural trajectory, there isn't anything that is unreasonable happening or has happened in the trajectory of ZK. And similarly, and it's a very similar primitive in the sense that it's not like encryption in general, right? In encryption, there is no computation. There is just a message you encrypt, and there are different forms of there are like RSA, El-Gamal, etc. But here there's computation. There are things that are dependent on the encryption time is dependent on the size of the computation, etc. Right? So it's very similar in that sense, and it's very likely that the switch from generic to specific is going to happen in the way that ZK has had. That's a thesis I think needs to be seen, but I think it's a primitive to take a bet on. It's a primitive, it's a tool that has huge power, especially given the fact that it aligns so well with what we want in the crypto space. So that is my bet, and I think this is all I had to say. And here is, this isn't something that we are building, but this is something that is very interesting, and likely the world will focus on this primitive, but what we are focused on is making every computation be done on the ZK as a substrate, and that is Forma. Again, call to action, request for call to action is please reach out if you're building anything in ZK. And like I said, we are a universal proof generation layer where the specific headache we take away is that you don't have to worry about putting together your own infrastructure. You don't have to worry about the way you incentivize these provers, etc. We give clean SLA guarantees on proof generation time and proof generation cost, and that's us. We are a universal proof generation layer for any proof system. That's it from my side. Thank you.
Thank you, Vanishri. I think we still have about 10 minutes, so let's take any questions. Ariel, go ahead. Can someone pass him a mic, please?
Yeah. Do you have ideas of what that would look like, that secret that your grandchild has that nobody else has?
I think it's a systems question. Maybe Web 2 will connect to Web 3 here, perhaps, as a starting point where you show your sequence of birth certificates and say that, okay, this person is Alice's child, this person, and so on. You show that, and you digitize that in some manner, and that can be a starting point. And that might enable projects to be built in our world where there are identity projects, of course, and that can be a motivation for these digital identity projects to add this feature where you also prove that who your ancestors are. I was just talking to a team, and it seemed like people were building like these parts of the puzzle without knowing what can be enabled using these parts of the puzzle. I think it was Provably and ZKTLS, and ZKTLS is part of the world where Web 2 comes to Web 3, and this data that can be proven, you can have proofs of SQL query responses using Provably, and so it seemed like a similar thing might happen here, right? Yeah.
Thanks.
I think just pass it to your right.
So maybe, but what he said, and I think that like all of your examples, they assume some kind of cryptographic society where we know what is the, I mean, court has public-private key, and also there is a way for this to evolve. So in the future, you know that this public key is of a court because it evolved from some kind of definition. So from what I thought, it's all kind of assuming cryptographic society, right?
I'm not sure if I completely understood your question, but if I am to repeat it back to you, you're saying the evolution of encryption as a methodology, and what about cryptographic society? You said, sorry.
So, I mean, you in all the examples you assume that not only that all the institutes have public-private key, right? That's one assumption, which I think does not exist. That's one thing that I would call the cryptographic society. And also somehow you assume that, I mean, you know, something can be open with a court order. You assume that it will also happen in the future, right? So it might be a new court that we don't know yet, which will have a public-private key, and somehow the proof would be able to know that this belongs to a court. So, but maybe the question is too general and not relevant. Sorry.
No,
I think if you're thinking along the same lines that I'm thinking, maybe what you're saying, it's not totally clear to me in this example of, say, the granddaughter, that it would say you do have super efficient general witness encryption for any NP. It's not clear that it would be easier to move the billion to the granddaughter safely than with witness encryption than with a digital signature or ZK snark. Because this problem of how to make sure that only the granddaughter has this secret, like, it seems maybe hard. I think that's maybe what you were saying. Yeah, but I should give the mic to.
And I think we have a question at the front here. Okay. I think, okay, lots of questions. Exciting.
Is it my turn? Is it me? Okay, cool. You know, this is a relatively new idea and actually very exciting, I think, for many people in the room to hear about witness encryption. Would it be possible to do something like, create a math prize, right? Where, it's like some sort of smart contract or something, right? Which has, a wallet, crypto wallet, and someone would have to submit a proof for like a mathematical conjecture for which there's no proof today, right? But like witness encryption would be able to like process that proof and say, or we're unlocking, like the person who knows that proof, unlocks the money.
Actually, that's a very cool application. Reminds me of that, isn't there this set of math problems? Right, where somebody who solves these problems will get the jackpot, right? And I think your example, the way you're thinking will help create a system that is resilient to chances like the person who's holding on to this treasury, or the committee that has the power to deploy these funds, right? There are no bad actors there, that they are trying to understand, trying to steal something and take the money. So there is no middle intermediaries.
Well, what's cool about this would be like, with like committees and stuff, you mentioned like corruption, right? If you had a prize that was open for like hundreds of years, right? Like this is a prize you could leave up essentially like forever, right?
I didn't understand the comment. What about?
I was saying, like you mentioned, there's millennium prizes in math, right? If those aren't solved for like hundreds or thousands of years, right? Like all those committee people will be dead by then, right? But with like witness encryption, like that prize will be there forever, right?
Yeah, and also no operational cost for people to keep a tab and secure that money.
Okay, next question from Damien.
Hi, awesome talk. I'm here, by the way. Yeah, so it feels to me there are two kinds of applications of witness encryption. One category is the one where we don't really assume the encryptor, the person who encrypts, is honest, and the other category is about that we actually need a proof of encryption. So the example you mentioned is that, well, you want to leave something to your grandkids. So then, well, this is a gift from you, so we don't really need to check that the encryption is correct.
Right.
But there are these kind of applications like encryption to the future, where you encrypt something and the encryption will be, the ciphertext will be decryptable after some block on Ethereum has happened. You can do that because you can write it as an NP statement.
Right.
So here you actually need to prove that the encryption is correct, that the encryption is legit.
Right.
So I don't know what's the state of the art, but is this problem of verifiable encryption, verifiable witness encryption strictly hard, or is it something that people have thought about? Or because I think the standard thing is that you don't really, we assume that the party encrypting is actually honest, and we don't care about that.
Yeah, that's super interesting. I actually don't know of any work. I think, what if you slap on ZK onto it? And I think the question is, can you do better? Right.
I think the next question, I think that will be probably last question. Any more questions? Last question at the front here.
Yeah, so my question is a bit related to the previous one. Is there any similarity between this type of schemes and like time lock encryption?
That is time lock encryption. I think it's a specific, it seems like it's a specific instantiation of witness encryption, right? Where the witness is that time has passed, seems like. But I don't know if that probably can be built in ways where you don't need the generality of witness encryption. That can come to the second part where you're building something specific, and that seems to have a lot of usability.
Okay, amazing. Thank you. I think that's the highest number of questions we've had today. So well done, Vanishri. And everyone, please give a big round of applause. So now we have a 15-minute networking break, but please make sure to rush back for the last talk of the day from Orest, one of the ZK Warsaw founders. Thank you so much, and please rush back.
is it too much work with the mics?
So basically, like, it's not like it's completely fine. Like,
Yeah.
will is low, isn't it? I think you have a lot of questions. Everyone, please stop making your way back to the main stage, the side stage, or the workshop room. If you're in the networking area, please stop making your way back.
Wow.
Everyone, please stop making your way back to a stage, a main stage, side stage, or workshop room. Keep the door open. Yeah. Everyone, please make your way to the main stage, side stage, or workshop room for the upcoming talks. We still have a few talks left before the end of the day. On the main stage, we have Unifying Ethereum with real-time proofs made possible today thanks to TEEs from Orest of T1 Protocol, one of our base sponsors. Please make your way to the main stage. Everyone, please make your way to the main stage, side stage, or workshop room. You'll have plenty of time to network afterwards. And we only have a few special talks left. Everyone, please give a warm welcome to Orest, who's one of the ZK Warsaw founders and also co-founder and CTO at T1 Protocol. He'll be delivering a talk on unifying Ethereum with real-time proofs made possible today thanks to TEEs. So everyone, please give a warm welcome and round of applause to Orest.
Thank you so much, Namita. Thank you, everyone, for having made it here and for having made it at 4:45. This is not remarkable. And today I'd like to talk a little bit about the project I've been busy with for the last 3 quarters or so. And this is going to be the inaugural, like the first time we are actually presenting what we've been researching. So please bear with me. If whatever that I'm talking about does come as a surprise, or you have something to add a question, please do raise your hand. We have microphones that will be given to you, and I'm happy to take questions as I go, and also I'm happy to try to adapt to where you guys are at. So maybe if I can ask a quick show of hands, who knows what a TEE is? Trusted Execution Environment? Okay, like half of the people here. Okay, cool. Yeah, that's a good start. I've just realized when looking at the slides, unifying Ethereum with real-time proofs is kind of ambiguous. I don't mean to unify Ethereum and real-time proofs. I mean use real-time proving, a concept we will come to talk about, in order to unify Ethereum's siloed ecosystems that we are dealing with now. Okay, so let's talk about real-time proving. Let's talk about how we can unify Ethereum, but in a way that's possible today, in a way that makes sense and can be achieved already. This is T1, one of the base sponsors as well. I'm Orest. What is Ethereum like nowadays? Well, we are seeing the result of what came to be known as a roll-up-centric scaling roadmap for Ethereum, which was basically kicked off a few years ago, more and more intensely and consciously in the ecosystem, that led to a shift from trying to scale Ethereum itself, the blockchain that we now know as the L1, layer 1, towards a system that allows for convincing Ethereum L1 about its state. That's what we got to know as L2s or rollups or other versions of L2s such as validiums or there's even more. Now, what this led to, it turns out, is we did indeed get to a situation where a user is able to trade on a DEX or get this NFT or like do some transaction on chain in one of those roll-up ecosystems at a low cost per transaction and at a high transaction throughput relatively. And so we managed to scale the performance dimension. However, this came at a cost of what used to be possible with Ethereum, what is kind of a promise, a very valuable property of a blockchain, which is composability, which is being able to have this one smart contract living somewhere, do something, and another smart contract living somewhere else use the output of the original smart contract as its input. And that in a way where the two smart contracts don't really need to understand each other. They don't need to be aware of one another. This is what we used to, or what we started calling the Lego blocks of DeFi, and what some people claim is the reason for DeFi's large adoption. And so this we lost. This is a property that as we add users to this ecosystem called Ethereum, which de facto means adding users to Scroll, the ZK rollup, or Arbitrum, the optimistic rollup, and so on, that this is a property we don't get to continue to enjoy in the same quality, in the same, for instance, delay. Now, I'm talking specifically about delay because this is something that is relevant with respect to how rollups work. Optimistic rollups obviously require a large challenge period, usually 7 days, in order to have a situation where a participant in Ethereum, an on-chain entity, such as a smart contract, can be convinced about the state of a given smart contract living in the optimistic world. Now, with ZK rollups, we have a situation where proving the state transition of that off-chain system can be done in a way faster way. We are talking about the order of magnitude of hours, maybe minutes, depending on the situation. So that sounds like a big improvement. Now, what do we mean by real-time proving? Well, by real-time proving, we mean a situation where such a ZK rollup, a ZK off-chain system, is able to convince Ethereum smart contracts about its state during the slot of the current block, or maybe the next block, like depending how you define it. So very quickly, the block time in Ethereum is 12 seconds right now. This means coming up with a convincing, so like a complete ZKP of some subset of this off-chain system, let's say of some Ethereum transactions, Ethereum compatible transactions, in a matter of few seconds. So we are not there yet. And because we are not there yet, because we need those minutes or hours or days to settle on Ethereum, to get out from this island of liquidity, this island of ecosystem participants, dApps, smart contracts, onto Ethereum, this creates this composability fragmentation. This creates this situation where I can't have my 5K USDC on Arbitrum and trade them for 2 ETH on Scroll. And maybe then use the 2 ETH on Scroll as collateral to take out a loan against DAI on Optimism. I can't do that. I need to do the one thing, wait for it to settle, so basically bridge this information into Ethereum, and then only can I take advantage of the output. So this creates liquidity silos, or islands. Now, an important consideration here, an observation we've been making, is that very few indeed users of the Ethereum ecosystem end up going and transacting on rollups. We see that less than a fifth of Ethereum, I think this is users or addresses, addresses are actually active on a rollup. Now, this can have many explanations. One of the insights we've been seeing recently at T1 is that people who deal with larger amounts, they don't want to commit to locking the assets in a given chain, in a given island. Maybe this missing liquidity, this is kind of a self-propelling cycle where there's little liquidity in a rollup, so the big guy with a lot of liquidity will not go there, so there is going to be little liquidity. And so this is a situation where we see like we clearly need some more scaling. We clearly aren't done scaling. Some would say, well, not a problem. ZK is getting fast. We have Ariel here who's been talking about speeding up FFT, whatnot, and there's all of those mathematical primitives and all of the hardware acceleration and those companies racing to and announcing a faster and faster approver every week on Twitter, at least. But then again, we need to ask ourselves, what is fast? Like, what sort of orders of magnitude are we talking about here? And how does this tie in with unit economics? Like, how do these costs and delays get distributed? And so, again, real-time proving. By that, we mean coming up with a proof for an Ethereum block in a matter of few seconds. And actually, because of timing games and kind of deficiencies of the current MEV landscape in Ethereum, this actually needs to be even faster if you want to actually compete. But let's say we are fine with having a few blocks delay, like a 20-second delay. Like, until we get there, we need to make significant advances, significant breakthroughs. And so my thesis is we need a solution that will bridge the time until then and prepare the ecosystem for growth in that direction. So what do we mean by RTP, real-time proving, that is made possible today? Well, I asked you about TEs. You obviously, half of you are familiar. The first answer that you will hear when faced with the situation where someone says, hey, let's fix security with a TE, will be, well, 0 days. There will be 0-day vulnerabilities, and all of the funds from a deposit contract will be stolen at that very moment. And that is very true, of course. Like, you should not rely on a TE alone. We should rely on a hybrid system. We should rely on defense at depth. And so what we mean by real-time proving today is actually a combination of TE, ZK, and economic security, restaking. SGX is obviously a good example here. Just a few days ago, there was a big piece of news that broke on Twitter about how I think 10-year-old servers with unpatched software and not applied security measures were vulnerable to extracting some ciphertexts. Still a way to go until you break and steal all the funds from the bridge, but then again, we don't have a proper system out there in the wild where a significant amount of funds would be at stake. So this is indeed something we want to design the system with. Like, we want to keep this in mind and design the system such that it may grow to trillions of value secured without having this prospect of once a given threshold is reached, a state actor will come in, break the key, steal everything. So how can we get there? Well, let's apply incremental RTP, incremental real-time proving, in a way that is parameterized and can react to developments in the market, that can react to developments in speeding up ZK compute, or maybe changes on the crypto economic front. And so incrementally, our vision is to approach this ultimate goal of what some people tend to call the unified states, or United States of Ethereum. Just some random logos here, and just random selection. And the question is, how do we get there in an incremental way? How can we get there without just having to wait until ZK is fast enough to be able to prove stuff in a matter of 1 second? Well, this is where our proposed design comes into play. And I'd like to get your input on this, actually. I mentioned I'd be happy to take questions as we go. So now comes the big design diagram, and I'm happy to be challenged on this. The idea being, let's start from the user that you should be able to see over here. The idea is the user would want to reach some goal. For instance, trade a limit order. So maybe Alice has 1 ETH and wants to get USDC, at least 3,000 K of that. She would go ahead and encrypt this intent of hers and send that to a set of validators that are being actively validated, like an AVS. You can think eigenlayer restaking, that are using the economic security of Ethereum stakers. Now, those validators, they only see the ciphertext of this intent, so they can't manipulate it, they can't extract value, and so on. They wait until a couple of intents come in, and they put that into a block of ciphertexts. Now, that encrypted finalized block, or like order finalized block, then gets shared with a TE worker. This worker is running in an enclave. In our case, we're using Intel TDX right now. And that worker will execute those intents that were encrypted to its public key. So only the worker with its private key can decrypt the intents. And they will come up with what we call integrity proof, which in its simplest form is just an ECDSA signature saying, hereby I, a TEE with this public key, sign off on this new state of the world, these outputs, this new state root. And it will also share the decryption key or some way for the validator to understand those ciphertext intents. And then will the validator be able to check, without doing much work actually, to check, hey, now Alice no longer has 1 ETH, and she has at least 3,000 USDC in this new state of the world, and this new set of outputs. This would lead to a match, what we call match proof passing. And this should happen in a way where this guy, this AVS validator, doesn't need to trust any of the stuff the worker is sharing with them. In particular, do they not trust the outputs, and they do not trust any plain text of Alice's intents unless they can convince themselves from the knowledge they gained here that the intents indeed match what the user originally wanted. One way of achieving this is using a commitment, a hash. And so then will the validator say, okay, I use my crypto-economic security power to hereby give the stamp of this new state, this new set of outputs corresponding, matching the user's intents. And this set of integrity proof, match proof, and bundle transactions will make its way to Ethereum, to the deposit contract on Ethereum mainnet, and be verified, and the update resulting from this will be applied to the balances for users in T1. Now, the interesting thing about this setup is that all of this can happen very quickly because the TEE is running off-chain, and because the AVS validator, running off-chain as well, of course, has very little work to do. They are checking a simple set of constraints. And because of that, we are able to push those items to Ethereum, theoretically on every Ethereum block, every 12 seconds. And this results in this composability that we are so much looking forward to, this real-time proving that we are looking for. Now, where is this ZK component, could you ask? Well, the ZK component is an additional measure that we are thinking of applying heuristically if ever this T1 contract on Ethereum, which in the end is the only thing you care about. You only care about Ethereum. You don't care about those off-chain systems here. If this T1 contract on Ethereum figures, hey, the outflows of funds from my deposit set is suspiciously large, I'm gonna actually require an additional piece to convince me on top of these three. I'm gonna require T1 protocol to submit a zero-knowledge proof for the suspicious state transition. And now this is something that can be easily parameterized in a dynamic way, such that as ZK becomes faster, the aggressivity or aggressiveness level of this heuristic could be increased, and also as ZK becomes cheaper, this is something that can be plausibly expected of the user. And on top of that, you can think of a setup where Alice has a choice. Do I want the result of my actions, of my intents, to actually have this additional stamp of security, and maybe I want that a ZK proof be required? The same could apply for DA. We could turn the system from an L2, like a Validium style L2, into something like ZK Porter, where Alice could say, hey, I want to opt in to paying a lot more gas in exchange for having all my transaction-related data live on Ethereum directly, rather than an alternative DA, data availability solution. Any questions about this? Oh, yeah. Can we have the mic, please?
I wanted to ask about generating the match proof. So as we generate it, we have a set of encrypted intents of the interactions that are going to be processed in that block. And while generating match proof, we are going to, I assume, assess those intents. And that's all we're going to do. So using your example, we are going to have the intent of selling one Ether for some USDC, let's say. And those two conditions are going to be fulfilled, but let's say there's going to be some sort of malicious worker that is going to fulfill those intents, but is going to also, let's say, take away 1,000 USDT. So what is stopping malicious worker from doing that?
Yeah, thank you. Very good question. So indeed, creating a match proof or checking whether there's a match between the set of outputs, untrusted, and the encrypted intents is not as trivial as it might look. What the validator will be doing is they will be checking each user's, like each diff's situation. And so if there ever is a malicious T worker that comes up with a state transition that should not be allowed, it would need to take money from one of the other T1 users' balances and put it to theirs. And this is something that would break the intent checking logic for one of those users. This is one situation that you could do, that you could check. On top of that, what you could do is already in this column, could the validator run some heuristics? Could the validator run some sanity checks and, for instance, have rules where it's actually them rather than the smart contract on Ethereum who say, hey, like a certain state transition may be interesting for more complex compute than just limit orders. Maybe a certain state transition or new state root looks suspicious and I'm not gonna risk being slashed for this. I feel like I need to require a ZKP on top. This is an additional security precaution that could be applied dynamically and that could incrementally lead to like make it easy to lean on ZKP or on other techniques such as FHE, maybe MPC at some point in an incremental way. Any more questions? Okay, cool. So if you want to learn more about us, by the virtue of doing a Verifiable Summit today, we actually had a natural deadline of launching our website. It's very freshly off the press at t1protocol.com. Let me know if there's things that don't work. It's literally been published a few hours ago. And also what I encourage you to do is to join us. We are hiring for a set of positions, mainly senior engineering roles, and we will be working towards getting a first testnet available very soon. So if you want to follow us and follow the journey, you can also find us on X and other socials. Other than that, hit me up. We have a booth upstairs. I'll probably be there for a few minutes after this, or you can come and talk to us after we've finished the talks for today. Thank you so much.
Thank you, Orest. And if you want to check out T1 Protocol on Twitter, I believe it's at T1 Protocol.
Exactly.
Okay.
T1 Protocol without a space, without an underscore.
Okay, perfect. And everyone, please give a big round of applause. And we'll be starting closing remarks very soon as the rest of the audience gathers on the main stage. Thank you. I'm gonna go in there and chat on. Everyone, please make your way to the main stage for closing remarks. This is the last talk of the day. Please make your way to the main stage for closing remarks. We're starting very soon. Everyone in the networking area, please make your way to the main stage for closing remarks, starting very soon. Everyone, please make your way to the main stage for closing remarks. This is the last talk of the day. Yeah, okay. I'll show you. You have to click next. So it's if you go and stand there, it's already ready to present. Everyone, please give a warm welcome to Hubert, CEO and co-founder of vLayer Labs, one of the organizers of Verifiable Summit, and he'll be delivering the closing remarks today.
Thanks for sticking around. Looking at the agenda, it has been a pretty intense day. So I have a privilege to share just a few final thoughts, trying to summarize what we've all experienced. Thanks for not leaving early. The temperature makes the temptations quite obvious. So I will try to be as to the point as possible. The main message of this very short segment is thank you for spending your time with us and deciding to invest these few hours in this quite interesting building, discovering so many important from the perspective of verifiability and from the perspective of blockchain, from the perspective of applied cryptography topics with us and our speakers. I just wanted to use this occasion to, besides thanking you, to share also a few pieces of data that we already know. Soon it will be verifiable. Most of them are coming from some sort of Web2 platforms. And we learned about web proofs a lot today. That was probably the most represented topic. So we will do our best to make sure that these will become fully verifiable during the next edition. So 121 has been reported as a count of unique participants today. Actually, we've been welcoming participants to almost 15 minutes ago, so I'm very privileged again to be speaking to some of us that joined recently. It's not as many as we have hoped, but given that it's the first edition in this setting, we are not forgetting about our origins and what ZK Warsaw have, the team behind ZK Warsaw have created. We are taking the mission of gathering professionals and enthusiasts that want to be the future of applied cryptography. But 121 is a great number, and we will do our best to grow our community in terms of number of participants, but obviously doing it when we are maintaining the high quality of the event. The second piece of data I wanted to share is that we had 29 presentations. We've been collecting some spontaneous feedback I do feel that at times we had too much to offer. It was impossible to be in 3 different rooms at the same time, and some of the topics really went extremely deep into the details. So again, I can only appreciate that you stuck around, and hopefully you have several takeaways and thoughts stemming from these presentations. Last item is also that it was important mission, and I believe when ZK Warsaw was brought to life close to 2 years ago, we really wanted to make this initiative as international, as diverse as possible. One of the metrics, obviously not an ideal one, is obviously engaging with professionals that are not just coming from Poland or from the region, and I believe we are making a great progress in this domain. 11 nationalities among our speakers, and a few more when we count all of our attendees today. And again, this is, for me personally, a starting point. I do hope that we will be able to run a global event like this in the next editions. So these are some of the data items that we already know. Hopefully you can trust me on that. Next year they will be fully verifiable, but for sure there are a few that we don't know. A few examples I was collecting on the corridors. Hopefully there is a counter of beers being enjoyed in great subgroups already, as I learned, but hopefully following this great session. On a more serious note, I do hope that all the discussions you had during the breaks, but also the ideas that you derive from the presentations of our speakers will convert into countless ideas that will take shape of some sort of projects or maybe companies. And that today we are putting a little seed into creating a number of important inventions and businesses out there. Of course, it's also my pleasure and my duty to thank our sponsors. We wouldn't be able to run this event without great support of our 3 lead sponsors, Opacity Labs again, Aleph Zero, and Aztec Labs. Thanks a lot for believing in us, especially since it's the first edition in this configuration. It was not obvious that we'll be endowed with generosity from these great projects. But not only them, we had also base and starter sponsors, Provably, AI, T1 Protocol. Hopefully many of you enjoyed that presentation by Orest just a second ago, and Golem there. We have been mentioning the important support from ETH Warsaw and ecosystem support program associated with Ethereum Foundation, very important partners. And I wanted to use this occasion to invite you to participate in the ETH Warsaw main event that is happening tomorrow and on Friday. But very importantly, we are also in the middle of Warsaw Blockchain Week. There is a number of side events, many of them hopefully you will find very relevant, and let's make the most out of your stay here in Warsaw. It's really important also to acknowledge all the hard work that helped us to produce this meeting for all of you. So I wanted to ask Agnieszka Deneve and her team for bringing the best standards of how these kind of events should be run. And their experience allowed us to create this event so swiftly, and hopefully you enjoyed all the little details that might be sometimes overlooked. Also wanted to pass big thanks to the ops team from vLayer, from one of my teams, as they were very passionately working on making sure that we will do this first show in the best possible way. The last thing I wanted to mention is just that as vLayer, we really do believe that the verifiable data infrastructure that we are going to introduce very soon, stay tuned for later this fall, is going to be an important piece of the Ethereum ecosystem. And obviously, we do hope that you will follow us and you will stay close to what we are building on the product front. But we do believe that the beauty of being in the decentralized world is that one of the values is associated with sharing knowledge, sharing insights, sharing some of the values that are very important for us. And this event is is one of our first attempts to make it relevant and accessible to others. We are planning to produce more events in different formats. We have just recently started or restarted a great initiative to group a Rust community here in Warsaw. So I do invite you to follow our X/Twitter accounts and all other social media channels for more info. We would be privileged and really happy to see you there and being active and benefiting hopefully from these initiatives. Thanks a lot for coming. I will not stay in the way of this beautiful afternoon/evening here in Warsaw, and hope to see you all next year.